to warmly welcome all geoprofessionals, where actually we have more than 100 registered participants. Since this morning we have 50, maybe more will joining us later on. And it's not only from Malaysia, but also welcome to our geoprofessional from Indonesia, Singapore, Brunei, India, Bhutan, Bangladesh, Nepal, Pakistan, and Nigeria. I'm very delighted that this event has successfully gathered the IAEG family together. Well, as part of our promotional initiative for ARC, today we're going to have 8 exciting topics from esteemed speakers, both local and international, which I believe will be introduced later. Okay, that covering the disaster from the importance of understanding the geology, how to prevent it, and also leveraging of new technology, including the machine learnings. And I would like to extend the thank you to the speakers for your time today. And I think I'm not taking more of the time. Okay, then I hope you will enjoy this half-day online seminar and bring back new technology that may contribute to the engineering geology aspect of our country. Congratulations to YGG and team. Thank you and Assalamualaikum. And also hope to see you next February. All right, thank you.
Thank you to IR Dr. Rini Asnida for the wonderful speech. Before I move on to our first presentation, so let me introduce our first speaker for today's seminar. Muhammad Farouk Shahmi earned his bachelor's in geology from University Kebangsaan Malaysia in 2016, followed by a master's in geotechnical engineering from University Technology Malaysia UTM. Currently pursuing a doctorate at UKM, he is an active geologist skilled in various geological areas, particularly in engineering geology, rock mechanics, and geotechnicals. He is an upcoming professional geologist to be registered with the Board of Geologists Malaysia (BOG). He leads as chairman of the Young Geo Professional Group of SCGRM under IAEG National Group. He is a member of multiple geological societies, including GSM, IGM, and the SCGRM, Malaysia affiliated with IAEG and ISRM. Now, without further ado, let us welcome Muhammad Farouk Shami Arifin to give his presentation titled Emerging of Widespread Debris Flow Disasters in Malaysia's Tropical Terrain, Understanding the Risk and Policy Intervention. Give him a round of applause.
Thank you, Puan Sarah, for the delight introduction. I hope everybody can hear me quite well. First of all, I would like to thank all participants and presenters to be able to join this seminar. I know this seminar is quite ad hoc in nature. We have not really distributed the brochure quite very early, but however, as Dr. Rini said, we have received a lot of participants, and it's almost now we have almost 190 registered participants, and we are hoping that everybody can learn a lot from this international seminar. And maybe if you have any question, please do ask by click on the icon to raise your hand, or key into the chat, and then the moderator or the MC will read the question for you. Okay, my the first presentation is about as per title, Emerging Widespread Debris Flow Disaster in Tropical Terrain of Peninsular Malaysia, Understanding the Risk and Policy Intervention. Actually, this presentation is a paper which my team and I have submitted and also published and presented at Torino, Italy, mid of this year, around June, mid of June this year, where we presented at Torino, Italy, debris flow hazard and mitigation conference. So I have not been able to attend. So Mr. Abdul Rashid, Vijul Abdul Rashid Jappar is the one who attended and presented the paper. And now I will I think not everybody is aware of the paper, so I'll be presenting this paper, but you can also find this paper in the online ResearchGate. Okay, so below is our team. It consists of Vijay Abdul Rashid, myself, and then we have Professor Emeritus Ibrahim Komo. He's very he's a past president for IAEG. I think I'm not mistaken, is for Asia. And then we have others. Datuk Zambri, Mr. Ibrahim, is from Department of Geoscience and Mineral, Malaysia. And we have also from university from UNITEN, UTM, and also UKM, which is a joint paper discussing in emerging of the debris flow in Malaysia. Okay, first of all, I would like to give some focus on this report by UNDRR, where on the right side is a figure showing the increasing risk of natural risk due to the climate change. As you can see, right now we are facing the climate change issue, not only on the rises of sea level, not only on the flood effect, not only on the glacial issues, but also on the natural terrain hazards such as landslide and also debris flow. On the left side is where we have to understand how, in the terms of the governance, we have to strengthen by compound cascading and by systematically understand the risk. And this is also from UNDRR. As you can see, we have four priorities here. Is a circle, is a cycle. 4 priorities. The first one starts by the understanding the risk, and then strengthening the disaster risk management. And then investing in the risk itself for the resilience. And number 4, priority 4, is to enhance in terms of preparedness and also build back better. This is already a established concept, but it's always ever changing. It is evolution by improving from time to time. So okay, this is a map, a very new map published in June 2023, where we can see the growth of population and the area where the population is affected by the disaster. As you can see, Malaysia, we are having population growth, not as much as other countries, but it is affected by a disaster. Beside under there, we can find Singapore, and then we have also Indonesia, where, as you know, the Jakarta itself, and then the issues in due to the seismic events and also the natural disaster. And this is where the map showing the disaster and then access to early warning system. Again, Malaysia is on the area where we have a disaster, but then we have a certain amount of early warning systems, but it's still not as comprehensive as compared to the disasters that have been happening in Malaysia. So we have to improve it on that particular area. All right, now we're going to the debris flow disaster in Malaysia. So previously, debris flow in Malaysia is not something that is commonly discussed or formally discussed in Malaysia because it is not something, as we know, debris flow is not something that is frequent. It is a low frequency but very high disaster destruction level. So as recorded since 1995, I think we should have recorded much earlier, but this is formally recorded by the Department of Mineral and Geoscience and also published papers. So a lot of events from 1995, which is the earliest event, and then on 1996, where we have a effect from the Greek tropical typhoon and killing of Sabah, causing 300 lives. And then it is almost annually, not almost annually, about 4 to 2 years annually per occurrences. But it is not, unfortunately, this event are not labeled as debris flow. It is labeled as something else. For example, in 1996, 29th of August 1996, it is labeled as a mud flood at Post Dipang, Perak, even though it kills about 44 lives, but then many more is missing. And it is not labeled as debris flow, even though because they are looking at the flood. The debris flow actually happens at the upstreams, but it is during the time the reports does not interconnect between the downstream event to the upstream event. And then we're going down all the way to 2009. A lot of it is labeled as tanah runtuh or landslide, even though in terms of the mechanics, it's actually a debris flow event. So on the right side, we have the photos in Post Dipang, where, as I say, it looks like a mud flood, but actually started from the debris flow. And then we have Peningau Sabah on the just below that, because of the Greg typhoon, sorry. And then we have Sungai Dui, Hulu Langat, Tasik Kenyir, Sungai Telemong, and also Sungai Lubuk Panjang. These four events is a very recent event, 2021 to 2022, 2 years back, and we are having a very widespread and also much more frequent debris flow event, and also the scale is much more bigger. And as is stated there, where previously we are facing a single channelized debris flow, or maybe is a hillside debris flow with the going into the channels, but now and it is a low frequency with high impact disaster, but now it's not really the case. Okay, going to the next slide. So we have one of few of the earliest events of debris flow in Malaysia. It started at Gunung Jerai in 20th of August 2021, where it's actually during that time is a COVID. Those who know who knows that the Gunung Jerai is actually a geopark, national geopark. So fortunately, it is COVID, so there are restrictions in terms of tourism. So when the disaster happened, the affected is in the area who living in the area, and then on the December we have a Bentong debris flow. Bentong debris flow actually occurs at the Bentong Raut Suca, really at the Titi Wangsa main bridge of Peninsular Malaysia, and it is affecting not only on the Pahang where Bentong is located. Actually, the debris flow affecting 3 neighboring states: Selangor, Pahang, and also some at the Negeri Sembilan. So and at the Kuala Lumpur and Selangor, at the downstream, they are having a very one of the worst flood event in Kuala Lumpur and also the Selangor state. I think most of you may know it is affecting our economy very badly. But then, if you look at the upstream, it all started with the debris flow. And then on the February, where at the Hulu Terengganu, we are having debris flow at one of our major facilities in Malaysia. And then we have Gunung Inas on July 2022. So also one of the biggest event last year, where it caused not only to the villages, but also to the affecting to the source of water from Gunung Inas to Pulau Pinang. And then and December, at the end of that last year, we have Batang Kali earth flow. So this one is much more smaller, but then it kills much more than the other four. So I will go into one by one. So at the Gunung Jerai debris flow, so this is what happened post event. As I said, it is a national geopark. Jerai is a national geopark, and then in terms of life, it kills 2 people, and then 2 are still missing. And then most of the facilities was destroyed and affected by the flood at the downstream, and the whole Yan district was affected and flooded. About 1,700 houses was affected by the flood, and then 120 shops affected by the flood. Based on the modeling and also the mapping, we have determined that because we are only for the time, we are mapping for 4 catchment only. If you go to the map and look at the Gunung Jerai is actually looks like an island of mountain surrounding by a very flat land surrounding the area, where the flat land you can see a lot of paddy fields. So it is like a mountain. So they have it. The mountain itself have a lot more than 5 catchments. I think about 8 catchments, and we are assessing only 4 of it because this 4 is one heavily affected by the debris flow. And based on the mapping and the modeling, we calculated that the volume is around 64,000 meter cube to 640,000 meter cube. And then calculating the total loss is about more than 1,000 million. So this is the where we have to understand the risk. So based on the mapping and also the modeling, we have calculated the max travel, 7 kilometers, and the max height of the flow height about 5 meters. The velocity is about 18 meters per second, which is around 70 kilometer per hour. And then because of the National Geopark, Jerai National Geopark, we have multiple rainfall gauge around the area, and also at the peak, where it's recorded around the time is about 280 millimeter per hour, or ARI 71. Yes, ARI 71. Now is the Bentong debris flow. This one is much massive. We have hundreds of single debris flow, all going to the major and causing flooding and also mud flood and also debris flood. Okay, so affecting 3 states, Bentong River Basin in Pahang, Hulu Langat in Selangor, and Jempol in Negeri Sembilan. And a total of 28 people die or missing, and also caused loss of more than 800 million within 2 days. So because this event, we haven't done any modeling because it's too big. So, but we have made some mapping and by aerial identification, helicopter and also satellite images. We have identified that at the maximum travel distance of 5 kilometers, and then the max height about 8 meters of the depth flow, and then a velocity of 13 meter per second. And this debris flow is actually due to the clash of a tropical depression and also monsoon surge. So we have a monsoon surge from the east coast clashing to the tropical depression at the center of the Peninsula Malaysia at the Titi Wangsa Ridge, and that clashing caused a very intense and very intense and extreme rainfall within a short period of time. Not only causing debris flow, but also causing a lot flood in Hulu Langat, in Selangor, some in Kuala Lumpur. Okay, the next one is at the Hulu Terengganu, or Tasik Kenyir. Where is it located? At the, it is a hydroelectric dam. We can see a lot of debris flow, but this one is actually in terms of size, is when we look at only at the dam area, it's not really as much as the others. But if you look at the satellite image or the whole overview of that district, the catchment, big catchment, we can see about the same as what happened in Bentong. And it's caused no casualty, but damages to Six Transmission Tower, and then caused major damage, not major, damage to the facilities. And then we have Gunung Inas debris flow. This one is much more major, and somehow it's kind of political. And by the modeling, in the event, it is affecting about 900 plus houses, and we have 3 facilities and 35 infrastructures was damaged. The bridge was collapsed, water tank was collapsed, and also we have there is one only one rain gauges, and that rain gauge also collapsed. And this not only causes flood to the villages, but it also cause connection between that particular village to the main road was also damaged, and it is not able to travel to the area, and they have to construct a bailey bridge, but temporarily, and it's still there. They are trying to clear out the sedimentations first, and then they will proceed to the construction of the bridge. And based on the models and the mapping, it is estimated that the total volume of the debris is 5.9 million meter cube, with the travel distance 15 kilometer. Because this debris flow is much more sandy and much more muddy, it can travel very far, and we have a maximum height about 10 meters, and the velocity of 29 meter per second. So it's very, very fast. It's about 90 kilometer per hour speed. And lastly is the Batangkali debris flow, which is actually quite small, but also it kills the most in the recent year, where we have 31 people killed due to because at the downstream we have a glamping site, is actually a recreation site. and it is occurring at the, because if you look at the previous event, it is due to the um, natural terrain. It occurs at the natural terrain, but here is occur at the embankment. So actually, you can find this detail of this report online. Is an open report of this particular disaster, and interestingly, there are no rain for 3 days prior to the failure. So you can find it, but the report to understand the mechanism much more better. But what I want to emphasize here is that the the type of the landslide is a debris flow or earth flow. Okay, when you have this particular disaster, the first thing to do for forensic studies is to do the mapping at the field. So the mapping at the field not only to go to find to understand the geology or the structure geology, we have to it's actually more into geomorphological mapping. So we have the first one, we have to look at the source zone. How big is the source zone? How far is it? Where is it? Does it located? And then at the transportation zone, what type of the debris, and is there any temporary dam formed in the transportation zone? Is it already burst, or is the temporary dam going to cause much more damage later on? So that's one the issues in the transportation zone. And then at the accumulation zone, we have to understand the boulder beds, find the boulder beds, look at the size, look at the type of rocks, look at the roundness, the angularity of the rock is also important. Okay, because for example, in Gunung Jerai, it is seemingly it is reported, but not is reported by a diary actually, a diary or a letter about 100 years back, where the letter stated that is actually um, they call it Bukit Reban, meaning to say collapse hill incident here in Gunung Jerai. So when based on that diary or letter, we look at the site and find there are um, uh, traces or evidence of paleo debris flow or paleo landslide because of the multiple layer of colluvium on the riverbank. So that is one of the evidence of that. And then we also have the look at the boulders, the shape of the boulders. Is it angular? Is it rounded? The rounded of the boulder, fresh boulders, indicates the strength of the debris, the energy of the debris, or and then the distance from the source. So if you have much more rounded boulder, then it is going to be, it is interpreted that it is having a lot of flowing in a very intense energy fluid, and this travel further from the source, and you have much more angular, maybe it's much more slower energy, and also it is much more nearer to the source. And then we have the impact at the riverbank, where eroding the riverbank, scouring the depth, the river floor. For example, based on our mapping in Gunung Jerai, in Inas, and everywhere else, we have identified that a single debris flow, not single, sorry, an event of debris flow able to increase, able to scour and erode the river bank, and also the depth of the river, the river floor, up to 10 times. So we have a river in Gunung Jerai. The prior to the failure is about 5 meter wide, but after the event, the river has become 50-meter wide, and the biggest the widest river is about 70 meters, from 7 meter or 5 meter wide of the channel. So you can imagine how big is the flow during the event. So a lot of other infrastructures at the site of the riverbank has been damaged due to that erosion of that debris flow. Okay, and then this is a typical forensic analysis, a geospatial analysis, where we identify the hazard zone, debris flow hazard zone. This is done by the Department of Mineral and Geoscience Malaysia, and then comparison of aerial imagery to identify the location of the landslide, and then the schematics of the debris flow. So this is the typical output of the simulation. So for now, in Malaysia, actually, we are the first one, I think the first one in Malaysia to apply RAMS, Rapid Mass Movement Simulation, debris flow, which is developed in Switzerland for the debris flow simulation. At least the first one in Malaysia, if not the first one in Southeast Asia. So I will prepare some paper for this. If you those who want to learn more about this simulation, I will presenting on the ARC next year, and maybe if I have the time, I will try to present at the GOC Thailand also in February. But if not, then it's going to be presented in ARC. I will present much more in detail for this model, for the how the model works and how we want to read the models. Okay. So this is a simulation for the Gunung Jerai. So you can see there are two catchment, but it is connecting at the accumulation zone at downstream. So this one is for the Gunung Inas as previously shown. And this is a schematic to understand the concept of that debris flow. So you can see laymen always say it is a water surge event, is or in Malaysia we call it kepala air. This is a very common event where we have a very high water, we have rains, and then cause increase of the river channel, and then causing flooding at the downstream. But water surge occurs very fast and subside very fast also, and the frequency of the occurrence is very high. But it is different from the debris flow. Debris flow starts by landslide at the upstream, and the debris of the landslide or is transported to the downstream and causing deposition along the transportation zone and at the downstream. So here we have two types of deposition in the accumulation zone. The first one is what we call as the debris deposition zone or debris accumulation zone. Mostly consists of boulders, cobbles, and gravel materials. But then because Malaysia is a tropical country, so the rainfall is usually continuously downpour and causing flooding that carries mud to the further downstream and causing mud flood. So usually laymen, they only look at the mud flood, but the started of the event is actually the landslide and also the debris flow. So this is the typical schematic for the Gunung Inas debris flow. So this is some scientific understanding of the geological disaster process. So we have type 1 to type 4, where the increase of rainfall from heavy to extreme. And then we have zones of incident. the starting will be the landslide, and then flow or transportation, and then the accumulation of the deposit or debris, and then causing debris flood, and then mud flood, and then river flood. So in terms of for normal debris flow or type 1, it's only stop at accumulation zone. But on the when the rainfall increases, it goes to the debris flood. What happened in Jerai, and then we go one step further. It's like in Gunung Inas, extraordinary rainfall, and then causing mud flood, and then lastly at Bentong, where it caused the whole catchment flood, the whole basin flood, river flood, where we have a very high and extreme rainfall. So in terms of processes, we have geological processes from the highland into the debris flood area, the debris flood zone. Most of it is geological processes, and further downstream is much more hydrological in nature at the lowland. So this is a simple figure to understand based on multiple debris flow that have been happened in Malaysia. This is a figure to simplify and to understand the geological disaster processes in Malaysia. So in terms of policy intervention, for the government, we have tried to we have structured two type of mitigation policy measures. The first one is a short term, where most of it circulate around the multidisciplinary forensic investigation, where Department of Mineral Geoscience has already started, and last year we have met about 9 catchment, and then this year another 7 catchment, 7 areas. Most of it focused on the Taman Ekorimba. Is a forest. What is the name? Is a ecotourism area, and then we also install AWS, automated and engaged for the time being, and then continuous post disaster clearing and mitigation, relocation from the destruction zone, and then public outreach. So public outreach, this is very important to acknowledge, to give understanding to the community, the differences between the debris flow and also the water search. And from there we conduct a lot of community-based disaster risk management, CBDRM. I think we have done more than 10 area for CBDRM, which is very good. Now most of those within the area community, they have at least a basic understanding for a difference between the debris flow and also the water search, and how to do action on their parts. And in terms of the long term, we want to we are doing right now National Geological Disaster Research Center, where it is actually already approved by the Prime Minister, and hopefully will be operate by early next year. And then we're implementing geological mapping for all the river basin and potential occurrences, setting up much better network of early warning system in the mountainous region, and ensure the multi-purpose structure-based mitigation. So for the long-term measures, all will be, we are hoping that all will be managed and structured by the National Geological Disaster Research Center. And of course, Department of Mineral Geoscience will be the leading agency and partners. I think I want to skip this one. This is one of the event of the CBDRM, where we empowered community, prepare manual for the if the disaster happen, and then disaster literacy engagement with the community and NGOs, develop local champions, and also early warning system. This is 6 elements that is important in CBDRM that we have been doing in Malaysia. This is one of the early warning system. And then I think this one I need to skip. So building tomorrow, strengthening today, empowering communities through disaster preparedness. So this is my tagline actually, to empower the communities, because our geologists, we cannot do everything by ourselves, because the communities are the one who are facing the disaster, and they are the one who needs to act on it. Thank you.
Thank
I
you.
think I exceed about 4 minutes. Maybe 2 or 3 questions.
Okay, no worries. So now we open for Q&A session. If participants may post your questions in the chat box, and we will read the questions to the speakers. Any questions from the floor?
Hi, can you hear me?
Yes, go ahead.
Okay, hi, I'm Intan. Thanks, Farouk, for sharing. It was a very interesting topic. My question would be on the CBDRM. Can you share a bit on the approaches that you guys take? Do you actually did a sharing session, or do you bring the public to site and actually see the possible signs of landslides, occurrences, or what? Thank you.
Okay, thank you, Dr. Intan, I think.
No,
Okay.
no, not doctor.
Yeah, Intan, thank you, Intan. Yeah, you are correct. Both of what you mentioned, we is incorporated with the CPDRM program. So the first part will be the education part. So we educate the literacy, disaster literacy. Okay, we look at the slide here. So here we the first you educate the literacy of the disaster for the community. We depending on the program, whether it is enough for 1 day or 2 days, maybe let's say for a good 3 days program, we started the first day will be started in terms of literacy, a lot of talk, a lot of engagement with the community, and also depend whether a disaster is already happened or not. If it's already happened, then we'll open to the community to share what happened to the destruction affecting their lives. We're going down to the women and child levels and the community for the women and child. Also, maybe the decision maker, maybe the head village, ketua kampung, to the unit uniform for example, firefighters, JEPAM, police. We engage them to give their thoughts on what happened in the area. If not, then we go to like a very theoretical part first, and then we bring them to site to see the potential failure, and also the what happened. If it's disaster already happened, then we go to the site where to show them the theory to link to the whatever on site. It's actually like a field trip to show this science and of that.
I see.
To show
Okay.
okay, and then after that, we do activities with the communities engaged, and then they are the one who, because they know the area better, because they are the community there. So we make an activity for them to uh, to find a way where the safe place and what they want to do, structure their planning and everything. So we are the one only to guide them, but they will be implementing. Okay, I hope that answers your question.
Yeah. Thank you. Thank you. Just one last query lah. Do you mind sharing your slide? Because actually I'm working while listening to your ni. Would love to be looking at it deeper.
The seminar is being recorded. I think we'll be
Oh,
share the
recorded.
recording.
Okay, okay, nice.
We will share the recording to the email. I will see how.
Okay, thanks.
Okay.
Okay, thank you very much for the question, Miss Intan. Also the answers from the speaker, but we need to continue our session now. Perhaps if you have any other additional questions, our speaker may be willing to answer the question through chat box or offline. So again, thank you to Mr. Muhammad Farid Shahmi for the wonderful presentation just now. Give him a round of applause. So now let me introduce our second speaker, Mr. Indra Andra Dinata. Scientific background is a Bachelor of Geological Engineering taken at the Institute Technology Bandung ITB. This knowledge was sharpened with a master's degree which also taken at ITB. Currently, he is pursuing a doctoral program at ITB to complete his education in the field of engineering geology. He has completed various projects, well, from local projects to national strategic projects, as well as international project which held in Indonesia. He received Associate Geotechnical Expert Certificate due to the engineering geology practice that already acknowledged in Indonesia. In fact, Mr. Indra was appointed as the youngest member of the Jakarta-Bandung High-Speed Railway Design Review Team. Apart from that, Mr. Indra is also active in research on landslide and rock mechanics at ITB. One of the results of this service is a book entitled Mengenal Aliran Bahan Rombakan dan Bahayanya. Now, without further ado, let us welcome Mr. Indra Andra Dinata to give his presentation titled Engineering Geology as Essential Cooperation in Rockfall Prevention. Give him a round of applause.
Hello, can you hear my voice?
Yes, Mr. Indra.
Okay, I will share my screen. Okay. Okay, can you see my screen now?
Yes, we can see your screen.
Thank you. So, good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh. So, today I will present about the engineering geology as essential cooperation in rockfall prevention. So, the highlight is essential cooperation because when we going to the Eurocode 7, the cooperation between engineering geology and geotechnical engineer for rock work or earthwork in the level of the highest level, level 3, it must be have an engineering geologist and that's work. So the engineering geology is an essential aspect for the geotechnical work. So why is engineering geology is so important? Based from the Terjagi, the father of soil mechanics, if you do not succeed in grasping the concept of engineering geology, you better keep away from earthwork engineering. Also, from the Muller Salzburg, the father of rock mechanics, rock engineering remains a sheer nonsense. Without engineering geology, it is even more dangerous than rock construction without rock mechanics. So, from these two experts, we have known that the engineering geology is something important for the earthwork engineering or maybe rock mechanics. So from the first, we should know the rock and soil, the difference between because we have rock, it's the engineering geologist, and the soil is the geotechnical engineer. So when the project or the earthwork begin, we must know the condition of our location. In Indonesia, for example, we have tropical wet climate. Then we have abundant rainfall in every month of the year. For the weathering aspect from this climate, we have maybe some ideal, the weathering degree. We have fresh rock and slightly weathered, moderately weathered, the highly weathered, then complete weathered, and the top soil of residual. So sometimes we have some ideal is likely some horizontal layer, but in some location we have slightly difficult or maybe something complex. Just like this, we have a sedimentary rock, we have not ideal horizontal layer. So in the rock mechanic, when we have the surface, we have residual soil just about 50 centimeter. Then we have get the rock when we excavate the slope. Then we have now the new rock slope pinion, which will be excavated. Then we have some rockfall potential. So the model, we must understand the rock. So the rock is, we have some intact rock, and then we have some discontinuity. And from the first one, we have a model, we call it Chile, that the rock we assume as continuous, homogeneous, isotropic, and linear elastic. And for now, when the modern technology takes place, we know that the rock is some to become a dynamic. It's discontinued because we have discontinuity. In homogeneous, we have mineral, we have some of the bedding, we have inhomogeneous. Then when we have discontinuous and homogeneous, the pressure will be different each direction. So we have anisotropic. And then we have the non-elastic of the pressure. So from this picture, we have some little aspect of the rock. We have intact rock without any discontinuity. So when we have the earthwork or engineering work, we have sometimes just get the sample from the intact rock. We get the UGS intact, and then we got the other properties. But from the model, we cannot using the parameter from intact rock from the lab. So we must convert it to the rock mass parameter. So to the rock mass, we should know which one dimension of our engineer work. It is include a single joint or two single joint sets or many joints or jointed rock mass. It depends our dimension of our engineer work. So for rockfall, in the rockfall we have some many joints maybe or perhaps in the jointed rock mass. So there's so many joint or discontinuity, then must be included in our analysis. So we should know the dimension of the block of the rockfall prone block. This we have the dimension of the rockfall potential, then we will calculate later in our analysis. So for the point of view of the surface, in the surface we have some roughness of our rock slope. So from the pattern of 1966, we have the slightly surface of the rock slope. We have average tips of 31, and the increase of the roughness, this, if we see as the pattern from the joint roughness coefficient is maybe in the scale of 20. We have average tip, it will be more steeper. We have 56 to 60 degree. So when we have in the surface, for the empirical reason, when the rock surface is smooth, the average tip will be lower. If the rock surface in the rocker, the average tip will be steeper. So that's the point. So what it's happened? It is because the internal property of rock, or it is affected by the discontinuity condition. So we'll be seeing the graph on the right. When we have the graph of shear strength and with effective normal strength, we have discontinuity. We have infill discontinuity. We have the low value of the shear strength. And but if we see in the rock mass, the fractured strong rock, maybe if we see the point fault, fracture strong rock, we have non-elastic, and we have some value of cohesion. We have a relatively high, but when we see the inside of the weak rock, on the height of effective normal strength, we have almost same value of shear strength, but the initial of cohesion is different. So that's the effect of the discontinuity. So in the investigation of the rockfall prevention, we should see the history of rockfall at the site location, the horizontal and vertical slope geometry, and then we have slope orientation and condition. And for rock and soil description and its engineering aspect. And 5 is description of discontinuity. That's the most affected of the rockfall. And 6 is identifying the rockfall source and failure type. And 7 is the type of rockfall movement. It is rolling, bunching, or sliding. So for the investigation, the discontinuity description, we should mapping the discontinuity. There are several methods that we can use. For example, is to using scan line. We straight the line of measuring type, then each discontinuity which crossing the measuring type, we describe it, every discontinuity. But based from the empirical, the only describe the discontinuity is only more than 50 centimeter. And the second method is cell mapping. When we have a limitation to scan line, maybe the rock slope is just 5-meter line, then we can get the limitation of scan line. So we can use cell mapping, or windows mapping. So we make some rectangle in the rock slope, then in the perimeter of the rectangle, when we have some discontinuity crossing the perimeter of rectangle, we describe it. So in the methods, the second method, it still have some limitation too, but we can use it when scan line is conducted. The third one is set mapping. When we have some photograph of the rock slope, then we get the some of the joint set, then we mapping the joint set, or in the joint set which will be affect the rockfall. And the fourth is the radar. We use some technology to get the 3D mapping of the rock slope. We got the radar. And the 5 is oriented borehole. It is common in the mining company. We got the borehole with oriented, so we can take analyze the condition of discontinuity about its orientation of the depth and the direction of discontinuity. So some of the equipment exclude the measuring tapes. We have some node, and then helical hammer, and GPS, compass, and then drone, and then Smith hammer. We use Smith hammer to get the approach to approach the UGS value in situ, but it's still intact. So some example of the discontinuity mapping survey in the datasheet from our laboratory in IAEG. So we use it based from the ICRM. So this is the right is the rock mass description datasheet. We describe the condition of the rock mass, about its condition, and then the rock material information, and then the UGS, how to determine it. Is it measured or assessed? If we measure, we using Smith hammer or needle penetration test. If the rock is weak rock, less than 10 MPa, and assess, we using helical hammer. When we hit the rock, and the helical hammer will give some assess value of UGS. And then the rock type, the description, engine helical description. So the rock mass information about the fabric, block size, and state of weathering. And then from the rock mass, we can just see what kind of failure mode from the site. So it is planar or toppling, then will be detailed in our analysis using kinematic analysis, and then we have the tile analysis. And then the orientation of the scan line, if we using scan line, about the trend and plunge. And the right one is the discontinuity survey data sheet. This is the parameter which will be described in the discontinuity. It's about the type. The type is from the fault zone to the padding. And the second is orientation. We using dip and dip direction. And then the persistence is the line of the discontinuity which we can see on the surface. And then termination, we see the end of our discontinuity. And then we have aperture, nature of filling, strength of filling, and then we have surface roughness and surface shape. And we will combine the surface roughness and surface shape to get the joint roughness condition. If the discontinuity is more than 1 meter, we have wavelength, wavelength, and amplitude. And next is water flow condition. We have the description below. It is very tight and dry, or it have flow of water. And then is the spacing of each discontinuity. And the spacing that we measure in the scan line is apparent spacing, because when we using the true spacing, it will not same with our scan line. So we using apparent spacing. So if we have the data of discontinuity, then we can conduct the kinematic analysis. And so for geotechnical engineering, they maybe this is a something new that they don't commonly understand. So we will explain what is the kinematic analysis, because we must understand the stereograph projection. So from the geotechnical aspect, when they don't learn about the stereograph projection, we try to make them understand, because this is something fundamental for them to understand the kinematic analysis, because we need to cooperation. So the geotechnical engineer not just accept our result, but they should know what why it happened and how it affect. So this is the safe graphical section. We have some stereonet, and we have some of discontinuous surface. We have straight line and the line of maximum depth. From this graph, maybe geotechnical engineers still difficult to understand what is the pole, what is the strike line, circle, and the alpha dip direction, and the beta of we can see the dip. It's still difficult. So we try to make some simplified method to make the geotechnical engineer understand it. So there's some 3D model of stereonet to make the better understand to get technical engineer. So it's allowing the three-dimensional orientation data to be represented and analyzed into dimensional. So the geographic representation remove one dimension from consideration. And an important limitation of geographic projection is that they consider only angular relationship between lines and planes and do not represent the position of the size of the feature. There's no position and the size of the discontinuity, just the orientation. So this is if we see in the stereonet, because we only see the southern hemisphere from the top. So how the 3D of the discontinuity surface can be represented in the stereo projection. So we make some breakdown in the triangular, black triangular. It is not arrow. It's what in the north and 0 degree east, and this is the geographic projection, southern hemisphere, and we have northern hemisphere. You don't use we use it for the polar, and then the discontinuity orientation. We have deep 55 degree, and the deep direction is not 0 degree. What it is. So if we see in the top view, so we have the stereoscopic projection of our discontinuity surface. So, and then this is the some example how to understand it. We have this. It is the 3D of the surface. Then we have tip. The tip is the crossing line between the surface, discontinuous surface, and the lower hemisphere, southern hemisphere. So we have this, and this is when we see in the top of view, we have this tip. So we have some line, support line to get the tip value, and then the tip direction is the north to the east. So we have the tip direction. So for the this is the to help the geotechnical engineer to understand the stereographic projection, because the stereographic projection is the fundamental to understand the kinematic analysis. And then we know the failure type. It is plane failure, or wedge failure, or topping failure, or maybe we have randomly oriented jointed, we have circular failure. So from this case, we have some of example circular failure. We have the withering, intensive withering. We have completely withered to residual soil of the andesite. This is in the Sumbawa Island in the eastern part of Indonesia. In the B, it is a plane failure, and you see into which failure, and the D is toppling failure. For the plane failure, we have orientation of discontinuity. It almost same with the slope orientation. For the wedge failure, we have to discontinuity. We have line intersection. The orientation of line intersection, it's plunge and trend. It's same, almost same with the slope orientation. And the D is the toppling failure. We have discontinuity orientation, the opposite side of the slope orientation. And maybe in one place we have all the failure type, because in the complexity of the discontinuity we have many jointed rock. So we have this is the circular, we have completely to residual soil, we have toppling failure, we have planar failure, and we have wedge failure. So maybe in some one place we have all of the type of failure, or maybe the dominated one failure. So it can be happen. So we must understand the orientation of discontinuity with the orientation of the rock slope. So for the case in Natuna Island, we have some detailed analysis. So from the rockfall event, we have this. Sorry. Okay, we have this. There in the before the lens rockfall event occurs, we have some plug in this location. Then it falling. We have still have some then from the event of rockfall, and the second is the block of the front of rockfall, but it is not very high, just 2 meters from the road. So this is still potential for rockfall. So this is the example in Natuna Island. Natuna Island is located between Malaysia Peninsula and Kalimantan. So it's on the northeast island of Indonesia. So we have this location is consists of church and flames. So we have very strong rock. The UGS value is about 90 MPa, so it's very strong rock. Sorry, strong rock. And then we have some rockfall prone blocks. We have 5 rockfall prone blocks. So we analyze it, the dimension of each rockfall prone block, and for we have 5, but we just will show 2 block to understand it. Block 1 is wedge failure. We have this is the rock slope dip direction, and then we have the discontinuity condition. We have 0, and then discontinuity internal fraction is 25 degree, and we have selective rate with GRC joint roughness condition is valid. So in this is the discontinuity which affect the wedge failure. This is the stratigraphic projection. We have this tail envelope to show that there is some intersection line. It's included in the tail envelope, so we have wedge failure. These are the 3D graph of the stratigraphic. So we have this block which prone to fall. So we have the geometry, and then we analyze it. We cut the mass of the wedge failure. We have 30 ton, and we have some problem when it's saturated. The safety factor is below 1, so it will be rockfall. And then rockfall direction is toward to the relatively to the south, but slightly to the western side, and the plane is 33 degree. So we analyze the energy kinetic, and the highest is the 2 slope. We have almost 9,000 kilojoule, and the translational velocity is more than 100 kilometer per hour. So it's very fast. And when we have car below, because below this rock slope is national road, so we have national road that designed to have average velocity is 40 kilometer per hour. So when the car is moving 40 kilometer per hour and cannot and will be hit by this rockfall, it will be destroyed. So it must be cautioned, and we must prevent this rockfall to happen, or we will make some prevention. So the other is block 4 planar. This is the highest of rockfall prone zone, and we have still same slope, dip, and direction. We have same discontinuity condition. Internal fraction is still same because we have same discontinuity condition in that location, and we have GRC is more smoother. We have GRC joint roughness condition coefficient is 10. So this is the block 4 planar. We have mass is 7 ton. It's quite big. When we have the density of the church is 2.6, so it's almost the dimension is 2 meter length, 2 meter 2 meter length, then 2 meter width, and 1 meter width. So it's quite big, and when it hit the car or some people, it will be destroyed. All the people we have casualty. The condition is same. When we have in saturated condition, we have heavy rainfall occurs in 3 days or more. We will have the saturated factor of safety is less than 1. So this is the total energy kinetic. It less than which, although it is the highest location because we have smaller dimension. in the block 4 planar. So we have maximum energy is 5,700 kilojoule, and the maximum velocity is 140 kilometer per hour. So this is basic or empirical recommendation for rockfall prevention. We have 5 blocks. So we have the biggest energy kinetic is the block 1 wedge, followed by block 4 planar. So from this empirical recommendation from the Climate and KHT 2014, we have deformable rockfall barrier to rockfall embankment. So because overlocation is very tight in the dimension of the road, national road, in the lower slope, we have sea, and the sea is very steep and will be very deep, and we cannot make some additional space on the lower slope. We just can add some additional space on the upper slope. But when we have to add additional space on the upper slope, we must excavate this very strong rock. So you must have some blasting or excavation procedure which makes some huge expensive. So it is very expensive. So there's some scenario to make some rockfall prevention. And this is the other empirical method from the Whiteside, 1986. We just see from the geometry of the rock slope and the height of the rock fall prone block. We have the very height is the 4 block planar and the 1 is which we have the ditch depth is about more than 2 meter, and the ditch width is the most width is the 7.6 meter. So it will be very long, and make new excavation about 7 meter is very expensive in this rock slope, very strong. We have 90 MPa, the value of UGS. So this is some future that we cannot occurs to. So what kind of prevention we can conduct in this location? So some scenario we have deformable rockfall barriers. We have the total energy. We have the highest is about 9,000. So we have this barrier capacity that we must install in this location. But the problem is the bearing capacity of 9,000 is very difficult to get. In Indonesia, it's very difficult. Maybe in the world, it's very difficult. But this is the minimum of bearing capacity that we can install to prevent the block 1 wedge. So this scenario is can be installed, but there's some node in this block 1 wedge. But we have the other scenario. We will using netting. We have active rockfall prevention. So we make some net in the rockfall prone area. So we divide it into 3 zones: zone 1 and zone 2 and zone 3. And the difference is the nailing interval. So the zone 1 nailing interval is 2.2 meter, and zone 2 is 2.5, and zone 3 is 3 meter interval. And then the problem for the netting, so the problem of the netting is expensive, still expensive, because we must get some bolting to install this rock bolt in the anchor to pin the net. We have very massive the rockfall, so it's still considered expensive. And then the third one is drapery. For the drapery, we just install some rockfall to pinpoint the net, which this is not considered an active protective but passive protective for rockfall. So we just let the rockfall happen, but we reduce the impact using this drapery or netting without any pinpoint in the rockfall. And the pinpoint only located on the upper part of the rockfall prone area. So we have some efficient energy, and this is the most suitable scenario. But for the construction work, it's still difficult to install because our construction equipment it just can be installed up to 24 meter only from this. But if we install higher than 24, we must have a manual labor. Then we have just like rock climbing to install the rock work. This is the difficult thing is the construction method. So now for now there's some additional scenario that I don't include in this presentation. We have some scenario to blasting 2.75 meter in this rock slope, but we need so we discuss with the geotechnical engineer because we have some rock slope like this. Then we want to excavate the dimension of the excavate. We cannot using benching because benching will make some rock fall will be punching, so it will be if we make some benching something like this, so the rock fall will be punching, it will be punching toward right to the road, so it cannot be happen. So we just make single slope, but the slope stability we will analyze it. And then for this the new geometry we have like this, the single slope. Then we have rock slope, rock fall. When we have hit the foot slope, it will be punching top. So we using drainage system. We discussed with hydrology team. So we make some drainage system on the maintenance area is uh, like a V shape, something like this. So when the rock fall is hitting the V shape of the drainage system, it will moving backward. As is something like this. If we have some ellipsoid geometry of the rock fall, when it hit the V shape of the drain system, it will toward backward. We still analyze it because now we have some paper in the 90s and that calculate the backward of this rockfall movement.
Hello.
Yes. Okay.
Sorry. Sorry, Mr. Indra. Actually, we have overrun the time. Oh, you already ended
Yes.
your
Yes.
presentation.
Thank you.
Oh, that's the last
So
one.
that's why.
Oh, sorry for intervene. Okay, so thank you very much, Mr. Indra. Just I may open one question, but if not, we will continue to our next session. So I think there's no question in the chat box. So apologize and thank you very much again, Mr. Indra, for the insightful presentation just now. Now, let me introduce our third speaker, Mr. Johan Rohani obtained his Bachelor of Engineering in Civil Engineering from Queensland University of Technology, Australia in 1996 and Master of Science from University of Warwick, UK in 2006. He has over 25 years of experience in fields of geotechnical and structural engineering with involvement in related projects both locally and internationally. He has extensive experience and is specialized in offshore geotechnical engineering, Over the last 10 years, is also actively involved in onshore slope-related geohazard assessment works. Besides consultancy projects, he has been involved in various research projects in the area of effect of shallow gas on soils, pile aging, remolded soil properties, lateral soil stiffness, predictive analytics, use of machine learning and remote sensing methods for geohazard assessment, etc. Mr. Johan has published more than 25 international and local conferences and also involved in reviewing international journals and conference papers. He is working member in the ISO Marine Soil Investigation, API ISO WG10 Foundations, and Standard Malaysia Offshore Structures Technical Committee. Now, without further ado, let us welcome Mr. Muhammad Johan Rohani to give his presentation titled On Detection of Active Ground Distress Indicators Using Multispectral Sensors for Landslide Forecasting. Give him a round of applause.
Thank you, Sarah. Can you hear me?
Yes, we can hear you.
Okay, I'll share my slides. Can you see the slide?
Yes, we can see.
Okay, thank you so much for that. Okay, first of all, Assalamualaikum and a very good morning to everyone. Distinguished chairman and distinguished industry experts who are here today. The topic of my presentation today is on the detection of active ground distress indicators using multispectral sensors from landslide forecasting. So I'm part of the team that has been working on this for the last almost 2 years now. And so some of my key members on this work include a representative from Aerodyne, who are actually the drone equipment and the machine learning service providers. One of them is Dr. Tiaga, and also representative from Geomapping, Encik Rashid Jaafar, and representative from our National University of Malaysia, UKM. So my presentation is essentially based from an engineer and industry practitioner point of view, right? So let's give it a go. Okay. So as a background, traditionally when we perform a geohazard assessment, we will be identifying the attributes and the features of a particular site. That could include things like slope height, slope angle, rock slip, and activities that are particularly experienced or occurring at that particular location. So these are particularly generally types of features that we record in the geohazard assessment. And after we record that, a location can be ranked as very high risk or high risk, right? So what we have seen in the industry is that this ranked risk has a common occurrence of being degraded even faster. And sometimes the lower risk can be failing faster than high risk. So all our work on assessment, sometimes along the way, have to be reassessed, and that assessment can take time and effort to do. And so we are puzzled by why these things happen. So that's the motivation of our work. So what we try to do in this work is to actually define certain attributes that we call dynamic geohazards or active signs of distress. So we assembled various terminologies that are common within the field of geology. And these are tension cracks, erosions, saturated ground, water ponding, and water seepages. I will go into a bit more deeper of these attributes later. But what we're saying is that these features, which needs particularly experienced geologists to identify, when we combine all these features, they have a tendency to expedite the risk deterioration of a particular site. So we call this active signs of degradation. So what we're seeing is that on top of typical features of a geohazard assessment, we have to also focus on signs of distress, which needs to be detected, because these are playing active role in changing the risk score of a particular location. So we postulate that with the use of multispectral sensors. Okay, I will go so a bit more detail about what are multispectral sensors and what they actually do. So what we're saying is that with the use of sensors, we're able to better detect these features. And if we can detect these features better and more accurate, we can timely predict the active signs of degradation. And in a way, we can forecast possibility of landslide failure or slope failures, as what Dr. Indra from ITB mentioned earlier. So what we're trying to do is, this is a tool that can bring risk to what we call ALAP, as low as reasonably possible. So that's the background of my presentation. Everybody knows what is landslide, and we usually attribute failures of landslide to rain, right? So rain has always been the number one criminal, if you can use that word, for a landslide happening, right? Rain results in increase in water table or pore pressure that could reduce the slope stability factor and results in failure. Okay, but we have seen that rain intensity and duration doesn't accurately predict failures, right? And rain happen often, but what does rain do to the features of the site? So what we're saying is that with rain, we should be monitoring the ground features due to the impact of the rain. And so what are these ground features that are due to impact of rain? And so we call this active signs of distress, right? So these features that are being degraded with the new trending in weather and climate pattern, we believe the degradation of sites can even be worsened over the future. And we believe that there need to be a tool for us to better identify these ground features which are effect of rain. Okay, so the good thing is that we can actually see these features on the ground, right? But the problem is when geologists go to the site, and for those who have done geological assessment or geohazard assessment, and they know that it can be rather arduous, and depending on your age factor, it could affect your interpretation somehow. Okay, so we are trying to minimize human errors, and that's why we are thinking that a way to monitor use multispectral, find a way to minimize human errors. And with the multispectral able to detect this some distress, we believe that this method can be a tool that a geologist or a geohazard assessment team can bring and make their assessment more effective. And with that data, we can have a predictive method in establishing potential hazard failures, slope failures. Okay, so just to also sort of touch base on what these signs of failures are, or active sign of distress are. So here, I'm not sure whether you can see my mouse. You can see a scarp, it's rather light there, but it's more of a linear feature. So we need to be understanding the kind of curvature and the kind of features that tension cracks provide, right? Then you see erosion, right? So erosion is a good indicator of potential failures in the future. When that happen, we don't know. So we are using a multispectral sensors to also detect this and predict, right? So erosion is something that we have to look for, right? But if you have to cover a lot of area, and if these are small areas, you might miss it. Okay, water ponding. Okay, to cover every inch is difficult. One thing about water ponding is that it's got some sort of circular shape, right? So you should be able to sort of codify it into a shape and the features of that water ponding, right? And then we have saturated ground. Saturated ground is again a very difficult thing to justify because different people have got different way of describing what is saturated ground, and different terrain have got different ability to store water. So we have to find a way on how to be able to better detect saturated ground. And once we standardize that, then it becomes a standard thing throughout all all the assessors or geologists visiting a site. And also water seepage. If it's a big water seepage, you can see it, but if it's light water seepage, you might miss it, right? And so if an asset is prone and sensitive to movement, these signs of distress needs to be established, because it provides us with the first signs before a failure or a stroke failure happen. So what we're saying is that these signs of distress needs to be better assessed, timely assessed, because these are precursor to failures. And if you can get that correct, we have a chance of predicting better landslide failures. Okay, everyone nowadays have maybe use a drone to some degree, right? Everyone can fly a drone. So we think that this is a tool that if attached to a multispectral sensor, it can be a very useful tool for a geologist to carry on site, right? So what are multispectral sensors? Right, multispectral sensors are actually a type of sensors that can detect certain wavelength of light in the red, green, blue range, right? I will talk about it a bit more detail later. So in a sense that if you have a tool that can be utilized to detect the signs of distress in a cheap and easy way, that will make this tool usable for the industry. Okay. For the purpose of our work, flying a drone is got to be at a survey level accuracy, right? So we set up a digital real-time kinematic space station, and that's a typical surveyor what do you call it, fixed station, a monument that we fix, and this monument with the drone, we are able to track an accuracy of about 1 millimeter range every kilometer. So we set up a monument for reference for our drone. We pre-plan the flight. So these drones fly in a program flight range. You can see this pattern here in the image. So that removes any error if you fly manually, all right? We capture, there's a process for data quality check. And so this got to be done by qualified surveyors. All right, a bit into the multispectral image. So this multispectral image, the raw data, constitute many data sets, right? The raw data sets is many data sets. So we need to get the right team to be able to process the data and construct the image. This red, green, blue wavelength from a certain nano range, nanometers in range. So different color bands. Say for instance, you have a red range. So that falls between maybe 400 to 700 nanometers. So another color band will have a different range. So combining of this color range with a particular algorithm will provide indices. And these indices, we have incorporated our experience, other colleagues' experiences actually in agriculture, where they actually look for plant health, and they have indices like normalized difference water index, right? Green normalized difference visual vegetation index, right? So these are the index that are formed when you combine these multispectral bands. And with the correct combination of these multispectral bands, you'll be able to detect things that are not seen by visual eyesight. And so what does it do? Multispectral, using the right bands in right combination, can detect, if trained, to detect certain features like active signs of distress. And multispectral is also able to produce detailed surface mapping, which has its own algorithm that can provide streamline order, contours, plan curvature. Because knowing the shape of these features is also important attribute for us to be able to accurately define what these features are. Okay, so in a sense, this is a summary of how you use multispectral image to be able to train it to detect features, active signs of distress, such as tension crack, water ponding, water seepage. And these features are precursors to potential landslides. Okay, so let me explain a bit more further into this aspect and combination of indices for us to define what are the signs of distress. Say for instance, in this table, if you can look at it, it shows the sign of distress are water ponding. So the water ponding, initially we started with NDWI, normalized difference water index, and a slope angle. And then we are showing that water ponding with our work now is mainly influenced by NDWI and not so much towards slope, right? Because you can have also water ponding in non-slope area, right? Okay, so to enhance this further, we have to enhance our current findings, we have to further filter and enhance our multispectral bands so that we select a particular range and a particular combination of red, green, blue colors that can better detect that feature. And so in the same way, we think that we can work on saturated ground, tension crack, erosion, and water seepage. So there are various papers that have been published, but I like to say that none of this has been able to combine these features and make sense of it for us to be used for better detection of signs of distress. So our work, I believe, in a sense, is a small breakthrough from my point of view to be able to use multi-spectral sensors to detect, right? Thanks to collaboration between engineers, geologists, and also machine learning practitioners. Okay. What I'm showing here, I've sort of, forgive me, I've sort of removed the key numbers because these are actually intellectual properties. I'm sharing you this sort of idea so that, say for instance, within a green yellow range, a color band, you have a certain range. Blue, you have a certain range. So this combination, all of this has got to be investigated. And which combination of this red, green, blue combination and its minimum maximum wavelength have got to be combined with various other indices for us to be able to sort of study whether those combination really are able to detect a geologist's findings. So what we do is that, first of all, we go to the site, we get the geologists to detect and identify what are the signs of distress. In this case, the geologists have indicated saturated ground. You see this pink line? Geologists can only sort of roughly define the boundary of this water saturated ground. But when we combine and make our studies, various permutation and combination, we're able to get the right indices, TVDI and NDVI, for us to be able to say that, look, hey, when we calibrate the geologist's finding to our multispectral finding, we can identify spot on where your findings are. Okay, one thing I like to note here is that, of course, multispectral can be more accurate and more definitive because you use sensors to detect. So it's not saying that the geologist is not done a good job. In fact, it is an excellent job that the geologists have done. Without the geologist's work, we couldn't calibrate. Moving forward, after we've calibrated this can be an automatic process of detection of saturated ground. So in a way, the industry, due to a practical need, requires this method because we have hundreds and thousands of locations that need to be assessed. And because of that numerous sites, it is very difficult to collect, to get the experts, geologists to be on site all the time. So with this method, we can get geologists with a certain level of capability with the tool, and they can provide the first line of assurance for detection. And it is very important that we detect these features timely, because only with timely detection can we have a tool to forecast failures. Okay, as an example of, again, I take saturated ground because I think there's too many combinations. So what happened is that on this slide, you can see the features on the left here. Okay, these are typical features as registered by a geologist. So this has been digitized, right? Once we digitize this, and so this is a typical image that can come up from a geology site visit. So SG1 is saturated ground, SG1. So we plot it on a photography map and plot the the geologist finding, and we superimpose our findings for the multispectral. So in a way, we have various sites that we calibrate, and after calibration, we have now reached about 70 to 80% accuracy in our detection. Of course, we can never be too brave to say that we can predict 100%, but with more data and with more experience and with more types of terrains, we can continue improve this accuracy of our prediction. Okay, I have just a few more slides because I don't think I want to take too much of your time. But what I've demonstrated is that in this particular case, in this particular example, multispectral sensors can identify saturated ground even under vegetation cover. So imagine if you go to site as a geologist, if there are vegetation cover, you might not be able to detect this. So with multispectral sensors, you can detect things that are invisible, you know. So invisible now is made visible, and that's a powerful tool. More calibration, more data, we can detect this kind of features and enhance the prediction better, right? Now we are proud to say that we can predict these 5 signs of distress to about 80% accuracy, right? I have to say that, you know, why we are choosing multispectral instead of LiDAR, because LiDAR light detection ranging system in our experience takes a longer time to process and needs special experts or practitioners to perform this LiDAR work. So with a multispectral sensors on a Phantom 4, any geologist can sort of fly it and store the data. So we believe multispectral sensors has got clear benefit in terms of detection accuracy, in terms of usability, friendliness, availability, for us, for it to be cost effective as a good tool for geologists to do geohazard assessment. Okay, I've got to just touch base here. The work is quite tedious because there's a lot of calibration, there's a lot of validation, you know. So this in a way a sort of give you a snapshot of the thing that we do. So we send geologists to site, you know, we ask them to independently assess the sites. Then we separately bring in the drone specialists with the multispectral sensors to take independent data. So certain data set we train and certain data set we test, right? So the testing set for our work for about 20 sites, it takes about 2 months to do. And then the data processing takes 3-4 times longer than that. And the challenge session for this is really challenging because we really got to spend hours to calibrate between the geologists and the engineers and the drone specialists. So in conclusion, I like to say that signs of distress needs to be monitored to ensure that geohazards affected at site do not further deteriorate a particular site to cause failure, right? So we can put in many mitigations, interim mitigations, but even interim mitigation has cost implication. So if we can detect it as a tool, as a monitoring as a tool, then it could be a way for us to assure our management and our team that with this tool, we have a way to accurately and timely predict failures rather than come in with mitigation. So from our work, multispectral sensors has proven to be able to enhance site surveillance to detect and quantify signs of distress. So work is still ongoing and work still needs to be done, but we have proven that to about 80% accuracy. So as a tool, it can bring risk to ALAP. So we can accurately say that this particular risk is ALAP. So the baseline is say very high or high. We monitor it, and because of that monitoring is constantly at ALAP level. Even if it degrades, we can monitor that and we can justify within the experts when to come in with the right level of mitigation. So what we're saying is that multispectral sensors can provide a cost-effective tool for the industry to try it out. It is the new way. Drones are new ways. There's a new business opportunity, but it needs capability development. And just as a kind reminder, it is not a silver bullet. It does not solve everything. So with that, I thank you. And if you have further inquiries, please do not hesitate to contact us. With that, I thank you so much. Thank you so much.
Thank you very much, Mr. Muhammad Johan. So now I'll open for any questions to be given to the speaker. Any questions from the floor? You can post it in the chat box.
Hi, Assalamualaikum, Mr. Johan. It's me, Intan. I would like to ask you on how many sites that you have been doing this multispectral analysis so far.
So for our work calibration, we have 15 test sites.
I see. So it's situated basically across Malaysia lah.
Yes, mainly in Sabah Sarawak location. Yeah.
I see. Okay, thanks.
Okay, I think that will be our last question. So thank you again to Mr. Muhammad Johan Rohani for the captivating presentation just now.
Thank you.
Without further ado, now let me introduce our fourth speaker. Dr. Reddy Dwi Kartiko is a senior lecturer in Institute Technology Bandung in Indonesia. His expertise is engineering geology. His education background from bachelor degree to doctoral degree were taken at Bandung Institute of Technology ITB in geological engineering. He has done so many projects, and the latest project is in the current year, the project called Engineering Geology for Basic Design of Legislative and Judicative of Next Indonesian Capital in East Kalimantan. Without further ado, I would like to call upon Dr. Randy Dwi Kartiko to give his presentation titled Seismic Hazard Analysis in Indonesia, the update and review of current application. Give him a round of applause.
Thank you very much. Testing. Let me check which one is slideshow. Okay. Yes. Okay. Can my slide is already seen?
Yes, I can see.
Oh yes, thank you. At several years, I think by accident, I worked a lot related with this seismic hazard and something. So then my experience is kind of changing actually from engineering geologist to this hazard assessment. Still engineering geologist, but several other projects is with this hazard assessment. So I'm kind of familiar with the development and the history with it. So I will share you about our history, and perhaps later on, can you also give us some perhaps vision or some comment or something that could help us to progress better for the Indonesian at this moment. As you know, perhaps several other country doesn't have a lot of earthquakes, but Indonesian does and still, and so we must have some robust analysis or something like that. So let me continue. This one is, so I think around 90s, we are, our preliminary analysis of our seismic hazard is started, I think, around 90s. Usually because we don't have a lot of expert at that moment, most of our expert is still in the graduate school somewhere, mostly in Americans or something like that. So we had a consultant. So a lot of work is doing with consultant, and the method is kind of, well, we can call it obsolete at this moment, but at that moment it's kind of good or something. So Golder and the others, so they do that for the analysis. So mostly from US on, but even in the US, the standard, I think the good one is came from California in around 97 or something. So in 95 or something, we still doesn't have a lot. I think in the whole world or something. So, but in near around 2000s, our public ministry works is because we must build some dam or something, and with our relation with another agency, so we have our new standard at that moment in 2002. It's already 21 years ago. 1726 2002. So this one is our mandatory at this moment. It took around 12 years, around 10 years to be adopted. So we need around 1 decade from this 2002 and people to understand and people to use this map that 2002. It's still very, very crude that in our standard at this moment, because we will have a more, well, that kind of things. So, and it's started our, well, now they are professors, but at that 1990 something they are starting go back from America, return from America and return from some others country, Japan and that. So they are building the new trend for seismic hazard. Most of them is civil engineers. So I myself is geologist, so and geologist doesn't relate with this at that moment. And then another history is yes, 2002 is kind of screwed or something, and then but ours water related agency in Indonesia building several and something, so they have their in our our name is Pusat Sumber Daya Air is what the center of research for water management or something. So they are the leading at that moment around 90 to 2000s, 2002, 2005. I think they have a lot, and I think their one works is 2008 or 2009. They're well known for the dynamic load for the Earthfield Dam or something like that. They have two versions for the Earthfield and for the rigid dam. So this one is, but based on this, we all use the Kramer book in 1996, the one that learned hazard analysis based on seismic. I think they all will read this Kramer. This like a Bible, I think something. And it's still used now for textbook or something, even though several properties is already updated and people use another methods. And in the other hand, ICOL, International Commission of Large Dam, is also active in Indonesia based on our public work agency. They are host now in public work agency in BTB, Balai Teknik Bendungan in Lebak Bulus, Jakarta. So if we want to know our standard or something related with dams or something, we go to this BTB and we have some review and something in always in that for the dam and related. So they already start from 88, very old, and now it's kind of obsolete method or something, but they update it every bulletin or something like that. They will update that this in itself. It is still quite inaccessible for a lot of us. So to access that, if we want to access that, we must join the iCold, or in the other hand, if we're not joined with the iCold, we go to by PTB and then we read the bulletin itself in PTB office in Jakarta. So, but yeah, that kind of thing. The story. Fast forward, now our latest standard is 2022. So we must revise our standard by every 5 years. So the aggregation map. In Indonesia, the word is Indonesia, but the mention is the aggregation map, and we have a lot of that. Our 2002 version is only have a picture for 500 written period earthquake, but this the aggregation map now we have around for 500, I think 2,500 return period earthquake, 1,000 return period, and also 10,000 return period earthquake. So we have grew a lot by several decades, of course. This one is now we use for our works in public and civil or something like that, and engineering geologists also. We have this for the earthquake load. We have these three standard. This one is the SNI of 2019. This is the third revision from the 2002 to 2010, and then 2010 or 2012, I forget, 2012, and then 2019. This one is for buildings. 2833 is for highway structures. It's now in 2016. It's due to revision, but not yet. And then 1860 is for geotechnical. This one is also related with engineering geologies and some for excavation and embankment or something like that. We use this for 1860. This is done. This achievement, if we open all this book and all this map, we will see our recurrent name in that, and that name is well known in Indonesia. Mr. Masyur Isham, I think. We all know him. I'm quite close with him. He always, well, kind of mad to me because what I've done is always wrong in his eyes. So, and I learned still a lot from him. So if you need to know and if you want to develop a better for your country or something like that, or of want or discussion or that, it's Pak Masyur is kind of accommodative with that, and we can have some collaboration. Usually, we always call Pak Masyur first, so he will handle everything, and then we build a team and something. Even this the aggregation map one, as a geologist, we are part in that, but the leader is the civil engineer. Geotechnical is from Pak Masyur Isham. He came back around 95 or something like that, or 94 from, I forget, this university, Michigan or something like that. And he bring this, well, the School of Americans. So the School of Americans is kind of strong in Indonesia. So in relation with the standard, because our standard is not, it's look robust, but it's not that robust if we do detailing. So we must see from the other standard, because American is like 1 decade or 2 decade ahead of us. So we use their standard from the highway, ASTO, and the ICE is, I think, more for the building or something. Right now is 722 version for the ICE, but some of us still adopt the 716 version. So most of our worker with this hazard will always, we must prepare this book when the reviewer come. So because we must open to and show them in which part that we use or something like that. The reviewer is kind of strict, so we follow by the books. And for upstream data, because our collaboration or something like that, and I think we have a long. I think every seismic hazard analyzed that done, they will always reference to this NGA peer from Berkeley one. So for earthquake based on earthquake source from shallow crustal one or something like that, we use this peer NGA West, I think, because the Cascadian range and the subduction in the west part of America. So we have that. And but now I think Pak Masyur already said that we also, the NGA also developed the NGA sub. NGA sub is for the subduction one. The NGA peer one, this one is for the shallow crustal. Usually we lack of the subduction data ground motion, so we use the Japanese one. Japanese one, I think Posai.jp or something like that. So we must browse that, and they are very robust also from the raw data. Raw data in Japan is kind of robust, but the analysis, well, it's different story, I think. So, but the data is quite robust for the and raw data, so not corrected or something. So it's kind of good for our research or something like that. But so we have the Japan and the other. So, but mostly we have this SGE and this ASTO one. So, but that one is kind of hard to chew for a lot of civil engineers and something engineering geologists also. So, for simple structures, we develop also not we, it's actually the Indonesian agency developed this kind of web-based interface for how big the load for our structure or something related with that. The lower one is Lini Bina Marga. This one is for highway, and then the other one in the right one is the RIS something is Puskim. Puskim is for Indonesia's pemukiman. This for housing and something related with that for public work agency. So the public work agency is kind of developed. Well, they already started like from 2002, so it's already 21 years, and so we have developed quite long, and then we already have this web base. But still, oh no 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 no. This web page is actually not as robust if you open the USGS NS HMP map or something. That one is much robust. With that web from the USGS, we can get in anywhere in America the response spectra. But in our case, we only have the spectra for PGA periods, short period, and long period. Short period is in 0.2 second, and then long period, and not the long period, and the SS short and S1 second and 1 second. So we have these three data, only 3-point data. But in USGS one, American one, you could have like 17 set of data or something like that. So from PGA until around 4 seconds response spectra. If you don't understand what's response spectra, well, go back to Kramer in 1996 or the books of that. So that so we still are lag behind in that regard. So this one is workflow example only, but this one is like one of my works or something. So we must conduct the assessment first. We must find where is the nearby fault and what is the subduction zone and their properties, blah 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 blah, and then there's seismic hazard is like conducted after that, probabilistic PSHA, and then deterministic is the based on determine that like the shortest fault and the nearest fault and the nearest subduction and something like that. And then we conduct the site specific. This one is already, I think, like everyone know if we do that, and then we must propagate the wave to the foundation, and then we have this envelope spectra design, and then also the modified time histories required for checking the structure. So we have this one is just I think because most of my work is with the dam, so this one is for the case of dam for 145 years of earthquake, and then another is like 10,000 years of earthquake, the maximum earthquake that could be occur. So that what next? I think we still use these American models, USGS one that already until 2014 they use Fortran, and now they migrate to Java. And I think we still have correspondence with them, even though most of them are already retired. So we have the new generation of the USGS related with this one. The other is from GEM, Italy, I think. But this one is like, I think we stuck with them around 2016 or 2017, I think. I don't know if it is still conducted right now. So in our committee, like in Pushka and PMKG, Badan Geology and the others, it's also in collaboration with those entities to develop more, because we must revise in every 5 years. So that kind of thing. So the discussion is, well, I'm open to any questions and any comment, and I think we need to learn if there is any another genuine or nice idea and how to develop a better this seismic one thing. Thank you for listening and see this. And if you have any question, please. Thank you.
Thank you very much, Dr. Randy. So now we're open for the participants to give any questions if you have. Yes, Mr. Johan, you may unmute or you can post in the chat box.
Yeah, hi Doc.
Yes, thank you,
Presentation. Thank you so much
Yes,
for
yes.
that. Just want to have a bit of your insights about this earthquake occurrences. In terms of sort of return period of these occurrences, right? Do you see that needs to be performed more frequent? Because do you see more occurrences of earthquake and that changes your return period sort of probabilistic hazard assessment? Can you comment?
Okay. So I think the concept of return period is actually is the probability of accidents per, I don't know. So it's actually the return period. The easiest one is if the earthquake occurred every 1 year, so that must be a small earthquake. Small earthquake is more frequent, right? So the bigger earthquake will occur rarely, like the Aceh in nine magnitude or something. It will be occur one in only 10,000 years. So the return period of such large earthquake is like only once in every 10,000 years. So that kind of thing. So that is the return period. So if we want to see the return period of the largest earthquake, so we must see the map for the 10,000 one. But return period is also related with the building history. So there is a calculation. So if I say the probability of the building will be hit by the earthquake with 10% hit with earthquake within this 5 years of 50 years of the building uh, building building age. So it will be calculated, but there is a calculation with it. It will be around 500 years return period that we must analyze for that building for the 10% probability. But if we want to have that the probability of the earthquake will occur around 2% within 50 years, it will be a larger earthquake. Perhaps it will be right uh, 5,000 years or something like that of the earthquake one. So we have that kind of calculations. And well, briefly, you can see this the book based on that kind, Dr. Johan. Thank you.
Okay, thank you, Doc. Thank you.
Okay.
Thank you, Mr. Johan. Is there any more question? We're open for another one question. Okay, so
Okay.
with
Thank you
that,
very
so
much.
thank you, Dr.
Yes.
Randy Dwi
Yeah.
Kartiko, for the
Thank
great
you.
presentation just now. Thank you
Yeah.
very much.
Yeah. Thank you. Okay.
Now we move on. Before we continue with our next presentation, we will continue with a video prepared by the Committee of 14 ARC of IAEG 2024. Hence, let us all give our attention to the screen for the video. Hello?
Suara tak ada.
Sorry, tak ada.
Yes, the sound is not
Apologize for the technical issue. We will continue shortly. Thank you very much for the committee of ARCIAED. With that, we would like to invite all of the participants here today to join the 14th Asia Regional Conference of IAEG on the 27th until 29th February 2024 at University Technology Malaysia UTM. With that, now we would like to take a few minutes for photography session. So I'll encourage all participants to turn on your camera. So we have 107 participants today. That is all. Turn our camera on so we can have a great picture together. Okay, so there'll be several times capturing the photos. I'll guide and then our committee will help to capture the photos. Okay, now smile. 1, 2, 3, ARC. Another time, 1, 2, 3. Again, last one. 1, 2, 3. Okay, thank you very much for all for joining us today. So without further ado, we will continue with our next session. Now let me introduce our fifth speaker. Mr. Abdul Rashid Jaafar holds a bachelor's in geology from the National University of Malaysia and a master's in applied geoscience engineering geology from the University of Hong Kong. His expertise lies in engineering geology, geotechnical engineering, hydrogeology, and geoenvironmental engineering for onshore and offshore projects. He played a significant role in Malaysia's infrastructure privatization in the 1990s and early 2000s and managed multi-million-dollar offshore oil and gas projects. He is a registered professional geologist with the Board of Geologists Malaysia and a subject consultant with the Department of Environment Malaysia. He's been deeply involved in various professional associations, serving as the president of Geological Society of Malaysia, and holding position in organizations like the Society for Engineering Geology and Rock Mechanics Malaysia. His international contributions include membership in IAEG Commission and on Engineering Geological Model and IAEG Commission 38 on rock mass characterization. So now, without further ado, let us welcome Pijul Abdul Rashid Jaafar to give his presentation titled A Conceptual Framework for Identification of Potential Debris Flow Area and Resolution. Give him a round of applause.
You can see my slide, Sarah?
Yes, yes, we can see your slide.
Okay.
You change to display mode.
Okay. Now, okay. Now the mode okay, it's a presentation mode, right?
Yeah, now okay.
Okay. Thank you. Thank you, moderator, for kind introduction. So basically, this paper presented in the coordinating CCOP of East Asia, Southeast Asia, and some part of the world for geoscience cooperation in Phuket last month. So I just want to share with you all the thought that we have, because due to recent incident of large scale debris flow, so there is a needs that we believe to identify potential debris flow area and as well as risk zonation in Malaysia. So this joint paper actually between the Institute Geology Malaysia, Jabatan Mineral Geoscience, SEGRM, Unit 10, and GMT Group. So it's not moving. Tak move lah saya punya slide. Kenapa
Tak move. Mungkin boleh try
Okay.
stop
Baru
balik.
move.
Okay.
Okay. The significant debris flow disaster, I think Farouk already present this in the first paper, so I will not touch detail. Basically the same. And then in 2021 and 2022, we have a large scale debris flow that never happened before. And Bentong debris flow, to me, at least a real mother of all disaster, because I flew with helicopter together with Professor Benkomo, provided by Forest Department. You can see the main range, Banjaran Titiwangsa, like had been scratched by a giant. So a big giant. So debris flow is everywhere, hundreds of debris flow and thousands of landslide. Right? So I skip this one. Farouk already explained. So this is the one that Farouk explained also earlier. Jerai debris flow, Bentong debris flow, Kenya Dam debris flow, Paling debris flow. And then this is the fact sheet of multiple large-scale debris flow 2021, 2022. I believe Farouk already mentioned about this as well. So I skip this one. So we have all the information, whether some is estimation, some is the actual information. And now, go to the problem statement. We have to answer to the policy and decision maker. Is similar event will occur? So that the question that always asked. If yes, where and when debris flow to occur? And then number two question is how to identify geomorphological. This is for the geologist or geotechnical engineer. The first one is questioned by the policy and decision maker. The second one, we have to ask ourselves how to identify geomorphological and or torrent characteristic favorable for debris flow to occur as initial target area for further study. And then the third one is what is the triggering threshold in terms of rainfall intensity, millimeter per hour, etc. And then I would like to, sorry, actually I'm in the workshop, so I can hear background noise. So not on the three element for debris flow to occur. This is based on Taiwan guideline. The three are torrent and slope characteristic, include gradient, curvature, etc. So in order debris flow to occur, you must have torrent or slope characteristic where favorable for debris flow to occur. And then second, debris. You must have enough debris, soil, loose rock, overburden, etc. And thirdly is rainfall intensity. You must have enough intense rainfall so that debris flow can occur. So these three elements that we use to look for those debris flow area that or potential debris area that we studied before. So I go back to Sri Prigi, Gunung Jerai, Kedah. This is one of the sub-catchment in Gunung Jerai, Sri Prigi. So we try to characterize the geomorphology with a cross section here, and then try to identify V shape, U shape, because this is important. Why V shape, why U shape? Because it's related with the formation of temporary natural dam that can burst later. So it will bring more disaster to downstream. And then, of course, U shape is more for deposition zone. So this is important. This okay, laser pointer. Like here, this table looks simple, but this is important. We try to what they call it, compile all these things so that we can predict better in the future where the potential zone of debris flow, slope gradient, decision zone. Because in Taiwan or in Japan, they already have slope gradient of initiation zone. What is the range? Transposition zone, what is the deposition zone? So then they can identify directly from topo map or remote sensing where the potential of this. But again, they are in the subtropical or temperate country, which is their canopy or vegetation is different from us. So we need to develop our own characteristic so that to suit our local. And then rainfall data also 200 mm per hour. I think based on a few study, we noticed that maybe 200 mm or 150 mm is the intensity that we look for, but need further study and confirmation also on this. And then this is Sungai Kepambaling. Also, we try to characterize the geomorphology of the catchment based on this cross section and then all these things. So we have to come up with a summary of parameter that we are look for. Okay, because this one later on we can use it to identify the geomorphological area that or terrain that potential for the flow to occur. This just to show one study that been carried out in Santubong, Sarawak, but this is rocky debris flow. Debris flow also you have rocky or sometimes set up muddy or even sometimes with the wood thing like that. So Sungai Mandi Santubong is quite special. It's very rocky type of debris flow. So we try to identify so whether in Sarawak and in Semenanjung is it similar or there is a different thing like that. So now I'm myself involved more project in Sarawak. We see more interesting geology and geomorphology in Sarawak that are, I would say, problematic to construction or development. Very interesting. I mean, maybe me or my friend will share other occasion. So this is Sungai Sedim. This is previously debris flow occurred, but this one is not occurred yet. But we try to try to map. This is a project by uh, Jabatan Mineral and Geoscience. So we are thankful to Jabatan Mineral and Geoscience so that we have the opportunity to study the area. So this is some data that we gather. We try to simplify actually in terms of geomorphology analysis, so that more geologists or geotechnical engineer can do this assessment. And then of course this is Cemurung Terengganu. Also similar, we already identify few patterns in terms of geomorphology and catchment pattern in interesting, because in here you have two deposition zone on the upstream and the downstream. So all these things is very interesting. So a lot of thinking process need to be done so that we can have a better um, what do you call it, approach in our assessment. So this just want to share. I think Farouk shared this earlier. It's been on anatomy zone and hazard zonation. Once we know the potential area, then we can expect we can do the zonation and geological disaster management map, so that they can help people living around that area in order to make decision where to go, how is going to be, thing like that, so that it helps people within that catchment. So this typical output study that being carried out is presented in IAEG Congress recently by James. I cannot go there. And then there's one thing that we want to share is the usefulness of guideline for natural terrain hazard study by GEO Hong Kong, where they classified hillside classification map. They classified the catchment into three: CD, channelized drainage, insist drainage channel with small single outlet, high entrainment potential; topographic depression, TD, limited drainage concentration with relatively small outlet, lower entrainment potential compared to CD; and open hill slope. Significant debris concentration, debris part is relatively unconfined. So this is one of study that we carry out in KL, one of the highway. So we try to classify it, so that is easier when we classify this catchment into the CD, TD, or OH. So then you can see that CD is where debris flow commonly occur, while TD can occur but not so common. Open hill is more for landslide. So then we can analyze geomorphology better using this approach, which I think very useful. And this is classification of hillside catchment from a guideline of natural terrain hazard study, T Hong Kong, second edition, 2016. So it's already explained here. Catchment characteristic in terms of topography, CD, uh, what is look like, TD, what is near, and then open hill in terms of topography. And then also drainage, debris concentration, discharge outlet, debris part is already summarized. So actually give us in initial thinking, mind thinking, so that we know when we want to assess the catchment or the sub-catchment. But this is for Hong Kong. Hong Kong is a subtropical, where the tree is not as dense as our hillside. So we need to have our own similar table actually, so that can be used directly to our situation. Wow, now the thing cannot move. Okay. So this is conceptual framework. So that you start with geomorphological and geospatial analysis. I want to highlight that remote sensing analysis on the yellow ni. Geomorphological analysis based on remote sensing data 25 features. This is what classification of hillside using the Hong Kong approach. And then geographical mapping and ground truthing. And this we need to do. Field mapping, of course. We need to identify all features on the ground, and then of course to identify landform on the ground as well. And then we include also mechanism and process simulation. So the one that we show you earlier is a simulation, debris flow simulation. As engineering geology, I think we need to do that so that we can explain to the user of our report how the behavior of the debris flow, if the debris flow occur at that area. And then of course lastly to develop mitigation strategy based on special result, develop recommend. So I think our government need to embark seriously on this, and of course it's already ongoing with the Pusat the Geological Disaster Center. We hope that more area that we can identify which is potential for debris flow to occur or not, especially area in where there is a people downstream. Yeah. Okay. Lastly, I would like to invite you all to 14 Association Conference. Video already shared before. So we have a speaker, international speaker. Please do join us. It's not easy to bring all these speaker to Malaysia, and then we have a group of speaker from all over the world. If you all don't take this opportunity, it's such a waste. With that, thank you very much.
Thank you very much, Mr. Abdul Rashid Jaafar. Participants may proceed to give any questions if you have. You can post in the chat box or you can unmute your mic. Any questions? Oh, okay, Mr. Johan, you may unmute.
Encik Rashid, thank you for that presentation. So, if I were to understand, um, debris flow is influenced by the geomorphology, the slope of the terrain, and the rain intensity, and the velocity of the flow itself. So my question to you is, the impact of this debris flow can be detrimental to populations and infrastructure. What are some of the ways that you think industry can adopt to make sure these events are better mitigated? Thank you.
That's why I think our study is very important, because first we need to predict where potential area that debris flow can occur. That is very important. So, and then there is an element at risk, the downstream. So that what we're going to do with the people downstream. In Taiwan, I visited Taiwan, debris flow area. They have what you call it, early warning system, so that the people can quickly move out from the area. Uh, but of course, the people don't want to shift to the location. They already stay there for many years. So that's one thing, early warning system. And then some area in uh, in Europe, for example, now the trend of mitigating debris flow is to what do you call it, to divert the if let's say the element at risk at the downstream of the debris flow parts, so they will try to divert the debris flow, not going to the element at risk area. So that is one of the mitigation. Now, of course, education, like Farouk mentioned this morning, we need to do community-based disaster risk management, so people aware what the difference between kepala air or water surge and debris flow. Water surge, the what do you call it, the danger will be the people inside the channel. But debris flow is not only the channel, it can overflow, and then people surrounding the flow part also can be affected. So this kind of, but I think structure wise, mitigation by structure wise is quite costly, especially if the thing happen like the one in Baling or Yan, or even in Bentong, because it's a very large debris flow. It's not like in Europe, in Alps, debris flow is very channelized, and then not as big as our debris flow in 2021 and 2022. So communicating with the people is much better. I hope answer that your question. Tuan.
Well answered. Thank you so much.
Okay, thank you, Mr. Johan, for the question. Any more question? Last one. All right, I think that's all. Thank you so much to Pijo Abdul Rashid Jaafar for the fascinating presentation just now.
Thank you.
Before we continue, all participants may grab coffee or snacks. Make yourself comfortable throughout the session. Now, let me introduce our next speaker. Dr. Kawin is currently working as a sessional lecturer with Newcastle Australia Institute of Higher Education and a freelance consultant. He is a professional geologist of American Institution of Professional Geologists, Chartered Geologist of Geological Society of London, and European Geologist of the Federation of Geologists Belgium. He is currently the president of Myanmar Geology Society Singapore and committee member of Society of Rock Mechanics and Engineering Geology Singapore. He received his Bachelor of Science in Geology from Rangoon Arts and Science University, Myanmar in 1976, Master of Science in Geotechnical Engineering, Master of Science in International Construction Management, and PhD from Nanyang Technological University, Singapore, in 1999 and 2005 and 2019, respectively. In Myanmar, he worked as an exploration geologist with Myanmar Oil Corporation and Myanmar Shell BV before moving to Singapore in 1993. He works here in engineering geology, geotechnical engineering, and rock mechanics fields involving with various projects such as geotechnical site investigation and instrumentation, underground rock cavern excavation, cut and cover excavation and tunneling works, and rock slope stability analysis, etc. Now, without further ado, let us welcome Dr. Kawin to give his presentation titled Engineering Geology for Successful Completion of Underground Large Caverns Construction in Singapore Sedimentary Rock Masses. Give him a round of applause. Hello, Dr. Kawin, are you there? I'm sorry, Dr. Kawin, we cannot hear you.
Oke, ada yang nanya ini. Ya, ini topik menarik, menarik ya. Ayo kasih pertanyaan.
Dr. Kawin, can you hear me? Okay, apologize for the technical issue. Before we move on, I think can we move on to next speaker first, and then we'll continue with Dr. Kawin next. Okay? Again, apologize on the technical issue. So now without further ado, I will welcome our next presenter, Mr. Dr. Imam Ahmad Sadisun is now an Associate Professor of Engineering Geology in Faculty of Earth Science and Technology, Institute Teknologi Bandung ITB, Indonesia. He received his Bachelor of Science and Master of Science in Geological Engineering from ITB respectively in 1995 and 1998. In 2004, he holds a Doctor of Engineering in the research area of rock engineering and engineering geology, especially related to swelling and slacking behavior of argillaceous rocks from Kyushu University of Japan. At present, he serves as the head of Engineering Geology Laboratory FEST ITB, research coordinator for landslide at Research Center for Disaster Mitigation ITB, chairman in Indonesian Society for Engineering Geology MGTI of Association of Indonesian Geologists IAGI, and representative members, president in the Indonesia National Group of International Associations for Engineering, Geology and the Environment IAEG. He is now also involved in a panel of experts for Construction Services Development Board, West Java Province, Dam Operational Improvement of Safety Project, and Commission for Safety of Bridge and Tunnel, Ministry of Public Work and Public Housing, Indonesia. Without further ado, let us welcome Associate Professor Dr. I.R. Imam Ahmad Sadisun to give his presentation titled Engineering Geological Aspects of Infrastructure Development, Land Use Planning and Disaster Risk Management in Indonesia.
Sorry, Dr. Imam, we can hear your voice.
Sorry, Dr. Imam, we cannot hear your voice. Maybe you can try change setting for your mic. Dr. Imam, are you sharing your screen? Sorry, we cannot hear you.
Imam.
I'm sorry, Dr. Imam. I think we can see your slides now, but we still cannot hear your voice. Is there anyhow you can change your audio settings, your mic settings? Okay, I can see you have unmute, but we still didn't hear any voice, Dr. Imam. Apologize to all participants. We will try to resolve this issue immediately. apologize again. We are very much apologize on this matter. Um, I would like to ask Mr. Shazwan, are you available?
Yeah, Sarah, I'm available.
Okay, so without further ado, we don't want to overrun our event, so I'll think we'll just continue with our next presenter first. Before that, let me introduce our next speaker. Mr. Mohammad Shazwan has over 17 years of oil and gas industry expertise, specializing in offshore and onshore geotechnical engineering. He is a staff engineer in geotechnical at Petronas, where he provides technical solutions by leveraging new technologies and technical resources in the field of onshore geotechnical and geohazard for infrastructures, as well as managing assets affected by geohazards. Now, without further ado, let us welcome Mr. Muhammad Shazwan to give his presentation titled Leveraging on Machine Learning for Managing Geohazard Impacts to Infrastructure. Give him a round of applause.
Okay, thank you, Farah. Can you see my slide?
Yes, we can see your slide.
Okay. Okay, Assalamualaikum and a very good afternoon to all members and participants for this pre-event of 14th Asian Regional Conference of IAEG. First of all, I would like to thanks for the opportunities given by the committee to invite us to share our experience in doing different things, which is leveraging on the machine learning for managing of the geohazard impact to structure assets. So, this paper actually was prepared by our team, led by Encik Johan and our head of department, Encik Azam, and consists of collaborated with data scientist experts, Dr. Ehsan Emirian, and also our colleague Hazwan Hizir. So as a background, geohazard risk has been identified as the major threat to the integrity of many onshore structure assets. However, in recent years, we are facing several issues on the geohazard, which is specifically on the slope failures suspected ataupun due to the rainfall intensity, high rainfall intensity, which impact the integrity of our structure asset, mainly in a few onshore pipelines. Therefore, the machine learning technology, which is have a data analytics capability, which can be leveraged and potentially enhance or explore the data capture from the assessments, monitoring, inspections activities from the site, which is can provide a clear understanding on the dynamic impact of the geohazard to the structure assets. Therefore, the incorporating of machine learning to enhance the current available system to trigger accurately and via early intervention on the based on the triggering mainly from the rainfall intensity, which is impacting the or resulting the geohazard risk can be intercept effects of further deterioration of geohazard conditions at site. So basically, this is the how rainfall induced slope failures, which is give us an initial ideas how we want to initiate this initiative, which is work with machine learning compared to the, I can say, a conventional method that has been used current and before, which is mainly with the high intensity of the rainfall infiltrated to the ground, and then therefore it's developed a poor water pressure and affecting the shear strength, soil shear strength, then resultant the slope failure. So that was the basic mechanism on the slope failure. So just to address a few general pain points in managing geohazards on our perspective, especially in managing our structural asset, which is number one is outdated of geohazard risk model. Of course, we have a current geohazard risk model. However, to certain times or durations, maybe we need to revisit the geohazard risk model, and it will take time and cost. And then the mobilization of resources to the area of remote and very challenging conditions, and no automated triggering system on the geohazards condition on site. And then the current repair or reinstatement at site is not been updated. No immediate guideline on managing geohazard issues, and we are dealing with a large volume of data with various formats. So the geohazard management system, which is derive the data from our inspection and monitor program has been used for purpose of machine learning. So basically, in general, we have two parts of data inputs, whereby first we conduct the LiDAR data acquisitions, and we will have the geohazard risk model using or derived from the LiDAR data. And then we have the routine assessment, which is we recorded the information or the condition of the site, sign of distresses, the geometry, and the current condition of the site in the performer. So all these data, we gather the informations, and we push to the dashboard to show the result. What we would like to focus is on the probabilistic prediction using machine learning platform, whereby in our previous or still we are using the current statistical model. So in this presentation, I will focus more on the prediction using machine learning platform, whereby issues affecting accuracy of machine learning is number one is accuracy of the data input, mainly derived from the performance data or data that has been captured by the site team that may not be very accurate to present the site conditions. And then the data collection frequency, because due to the way of collecting the data is via walk down or site assessment, assessments. So sometimes we are dealing with challenges to get a data timely, and then cleanness of the data itself in terms of geohazard parameters, sign of distresses, geometry, rainfall intensity, and the structure asset defects data. And then the availability of instrumentation data. Again, various data format includes images and numerical data. Different input parameters have a varying degree influence, and then output variable are not suitable to be used for the machine learning purposes. So why we use the machine learning approach? So machine learning basically is able to develop a geohazard risk score model and use a probabilistic algorithm to provide more representative geohazard model. So this is part of an overall system that makes system information available through integrated models and data with the purpose of providing the decision support. So mainly in order to produce or display the overall result or the status of our integrity of structured assets via digital twin dashboard, we need input that I've said earlier. And then on the machine learning portions, there will be competition models, development of algorithm, data transformation, and also search algorithm. And then it will push the output in terms of by visualizations, recommendation of the action to be taken, all related information, key informations, and it should be in automations mode, and it can be queries or search status. So I would like to emphasize on the advantages also by using this machine learning approach compared to the other or current methodology or approach. In terms of model flexibility, this machine learning are able to offer more flexible and it can handle more complex relationship in data. And then in terms of prediction performance, this machine learning approach is more concerned with predictive accuracy. So in other hands, we can have a qualitative accuracy evaluations when we're using to these with this machine learning approach. And then, of course, in terms of data, when we are dealing with the large amount of data, so machine learning can perform well with large data sets. And people also say that machine learning can offer a black box model whereby the internal workings are complex and not easy interpretable by other method, but with machine learning it can be done easily. And then, of course, in terms of feature engineering, it can involve feature engineering where algorithm automatically learns from the relevant features from the data, reducing the need for explicit the future selections. Okay, the predictive analytics on our geohazard risk using supervised method, whereby we have various inputs that has been pushed to the model, inclusive of terrain geometry, sign of distresses, rainfall intensity, material defect, as well as the consequences in order to get the risk perceptions or risk index of the asset itself. And then to train the prediction model by mapping from label inputs to until the outputs. So every input we will label, and then the result will be a probability of geohazard risk, which is we call it as a PR, whereby it's then used to derive the probability of failure or geohazard probability of failure ataupun POF. So just to share with the audience the example of our result using the regression method. We have tried a few methods, regression methods in our exercise. So at the end, we found out that the XGBoost regression method are performed the best, which is it fit lines very close to the bench line when it's using the trained data set. So which is resultant the R square of 75% of accuracy. So this is the example of site validation, real site validation that has been performed in order to to validate the result from the predictions of machine learning just now. So we have performed a few site validations. It is performed by geotechnical engineer, also geologists on site to revalidate or to assess back the site condition. Is there any similarity to the result that given by the machine learning? So as conclusion, machine learning can be leveraged on to help with timely and improve the accuracy in prediction of geohazard impact to infrastructure, which is continuous improvement can be made via the to increase accuracy of data input, which is in our opinion, it should be less dependency on human intervention, which is currently we are embarking or explore uh, another new digital technology, which is, has been presented by Encik Johan earlier, which is using multispectral sensors via UAV that hope can give more accurate and timely data that can be fed into our model and give more accurate result. And then more data from the instrumentation or geotechnical instrumentation and calibrated with the ground experience will enhance our model or detection as well as the prediction capabilities. So at last, we can invest in capability development with a new way of working. However, still, this technology is not a silver bullet where it can resolve all the matters. With that, I end my presentation. Thank you.
Thank you very much, Mr. Shazwan. So now we're open for Q&A session. Participants may provide your question in the chat box, or you may raise your hand to give a question. Any question from the floor? We still have time for question. Any participants would like? Okay, we have one from Mr. Muhammad Farid in the chat box to Mr. Shazwan. What is the accuracy you get based on the current prediction model?
So, like yeah. So, based on our current model that we have developed, the accuracy level we achieve is 75% at this moment. So basically, we compare or we train the model based on the our previous statistical model, and based on that comparison result to the baseline or train model, so we got these accuracy numbers.
Thank you, Mr. Shazwan. Hope that answers your question, Mr. Muhammad Farid. Yes, okay. Thank you very much. So do we have other questions to ask to our speaker before we move on to our next session? All right, I think that's all from our Q&A session. And again, thank you so much, Mr. Mohammad Shazwan Kamil for a captivating presentation just now. Now, without further ado, let us welcome our next presenter. Before that, I'll introduce again our speakers. Dr. Carwin is currently working as a sessional lecturer with Newcastle, Australia Institute of Higher Education and a freelance consultant. He is a professional geologist of American Institution of Professional Geologists, Chartered Geologist of Geological Society of London, and European Geologist of the Federation of Geologists Belgium. He is currently the president of Myanmar Geology Society Singapore and committee member of Society of Rock Mechanics and Engineering Geology Singapore. He received his Bachelor of Science in Geology from Rangoon Arts and Science University, Myanmar in 1976, Master of Science in Geotechnical Engineering, Master of Science in International Construction Management, and PhD from Nanyang Technological University, Singapore in 1999, 2005, and 2019 respectively. In Myanmar, he worked as an exploration geologist with Myanmar Oil Corporation and Myanmar Shell BV before moving to Singapore in 1993. He works here in engineering geology, geotechnical engineering, and rock mechanics fields involving with various projects such as geotechnical site investigation and instrumentation, underground rock cavern excavation, cut and cover excavation, and tunneling works and rock slope stability analysis, etc.
You have to
Without further ado,
Hello, can you see my screen?
yes, Dr. Kawin, yes.
Or you can see my screen right here.
Yeah.
Okay, so can you continue now?
We so yes, you may. Now, without further ado, let us welcome Dr. Kawin to give his presentation titled Engineering Geology for Successful Completion of Underground Large Caverns Construction in Singapore Sedimentary Rock Masses. Give him a round of applause. You may
Okay, thank
continue.
you very much. Sorry for inconvenience caused. Okay, so the firstly also my I cannot connect the camera, so this why I cannot show my face. Or apologize for that. Okay, so today my topic is Today, my topic engineering geology for successful completion of underground large cavern construction in Singapore sedimentary rock mass. Okay, totally 62 slides, but don't worry. I try to finish within half an hour. Okay. So this all my presentation it come from these two paper. One paper is you must go to the GG. Okay, you must have the asset. Second one is a free download. This is my PhD thesis. Okay, I got PhD in 2019. Now I'm 68 years already. I got my PhD in 63 years. My age of 63 years. Okay, if you have any question, you can email to me here. Okay, this is my email address. Okay, so this is outline of presentation. I have eight subtopic. Okay, so before go on, okay, for the underground excavation, okay, mostly for the road tunnel and train tunnel, we are using the tunnel boring machine. Okay, so this is the very advanced technology. This is a one method. Another method is 3M plus one. Okay, so this one you will see the drilling, then after that charging, then after that blasting, then after that marking out, then we apply the what we call shotcrete and robo for rock protection. Okay, between these two methods, this one is not good for our job for us geologists because we cannot see the raw face, we cannot see the outcrop. Okay, only this drill and blast technique we can see all the raw faces. Okay, so this my presentation it come from the Jurong Rock Cavern project. Okay, so this is we have this is we excavated for the wide storage cavern. Okay, so this from this diagram you will see there. So we have we have the two level. Okay, so we have the access shaft, excavated access shaft. Then after that we have the two level. Okay, so one level around 100 meter below existing ground, another level is 132 meter below ground. Okay, so okay, so this is where the location. Okay, so this is the Johor Bahru. Okay, so this is Singapore. So this project is here. Okay, actually this area is actually earlier is a small island. Now later we have reclaimed to make it one big connected islands. Okay, so this Jurong Rock Haven is actually totally under sea. Okay, so this one you will see the layout. We have the 5 Y storage given for the store for the Y and gas. Okay. So this is the short point of my presentation of this project. Every project we need to understand the integral and raw mass property. Okay, so this one before start the project, we are doing the 3 phases of site investigation work. 3 phases or site extensive site investigation. We did a lot of borehole, particle, sub-horizontal, inside you testing, parameters, something like that. Then after project is awarded to contractor, during the excavation and construction phase also, we dig the geomechanical properties, okay, for the more and more geomechanical properties. Then during the excavation, we dig the geological phase mapping. From the geological phase mapping, we identify the geological strength in there, technical quality index, Q value, RMR value, something like that, all the parameter. Okay, so this is the new Singapore geology. Okay, we have upgraded in 2021. Okay, so this is the all the here this is sedimentary rock, this is the igneous rock. Okay, so Jurong Rock Event Project under the sea, we excavated in the sedimentary rock masses. Okay, so this paper about this geology condition I have submitted in the Bulletin of Geological Society of Malaysia in 2018. Okay? All the rocks are formed by the pepperite at the contact boundary. It means that you see here, this what we call Blau Ayi Chawan formation. Blau Ayi Chawan formation, we have sedimentary mudstone. You see here the black color mudstone. This black color mudstone and this light color pyroclastic rocks are interbedded. This interbedded, they are formed at the same time parallelly. So this one, they are the same depositional volcanic activity. So this all are I have interpreted as this is the pepperite. Pepperite is the process. Okay, the mudstone and volcanic lava flows are formed together when the mudstone is still in the swine condition. Okay, so no, mudstone haven't become the rock yet. Okay, mudstone and the pyroclastic lavas are formed together. So this is we call the pepperite formation. Okay, so for the general geology, this area earlier I have explained that this is a reclaimed land. Okay, reclaimed sand is around 15 meters. After that, we have the residual soil. Then after that, weather sedimentary rock. Below, after weather sedimentary rock, we have the good fresh sedimentary rock. But sedimentary rock, but actually they are intercalated or interbedded with the pyroclastic rock. Okay, so this one, we have 2 levels of excavation. First level is 100 meter, another level is 132 meter. Okay, so second topic is we measure the geomechanical properties of the sedimentary rock mass. Okay, during the drill and blast excavation, after each excavation, we did the geological mapping. Okay, so this is the form of the geological mapping. Okay, so this is the phase. Okay, something like here, dry and padding plane and something like. Then after that, we need to measure all the discontinuity parameter. Okay, B mean padding plane. After that, joint plane. Then after that, from here we have to record down the 6 parameter to calculate the Q value, something like that over here. So we did every phase, we did the geological mapping. Okay, then after geological mapping, from all the data, we have draw a something like kinematic analysis. Okay, from all the joint data, we use the deep software. Okay, deep program raw science. Okay, from there we can interpret that we have the one betting plane. After that, we have the three to four prominent choices. Mostly they are in this direction, not east or not northeast direction. Okay, so another one is we have measure the in situ horizontal strike. In situ horizontal strike measurement is very expensive. Okay, Singapore we cannot do. We need to hire from the overseas contractor. Okay, so this one we did only for this major excavation project only. So we dig the inside use strike measurement in 3 borehole. Okay, so combined with the borehole televiewer. Okay, from the borehole televiewer, we will see the existing joint plane, and this is the new plane. Okay, we apply the high water pressure to open the existing joint or to form a new joint. Okay, from this water pressure, we calculate the horizontal strike. Okay, so this in Singapore, roughly horizontal strike ratio is, here you will see the sigma h. Sigma h means maximum horizontal pressure, minimum horizontal pressure, and particle pressure ratio is 2.2, 1.8 to 1. Okay, particle is 1, horizontal maximum is 2.2, median is 1.8. This ratio, the horizontal stress ratio is important for the design for the what we call robot and protection, because we need to know our surrounding rock is very high stress condition or medium stress condition. If high stress condition, we need to apply very strong support. If we have the moderate or low stress condition, we just apply for the low low support condition. Okay. Then also this our sedimentary rock horizontal strike direction is roughly northeast and southwest direction. Okay, so this direction is important to design or to choose the tunnel alignment. Mostly tunnel alignment are perpendicular to the maximum horizontal strike direction. So that's why we need to measure the horizontal strike. Okay, the next one is the strength properties or integral by Boileau test, uni-axial compression test, tri-axial compression test, Brazilian test. Okay, so here, okay, you most of you may be familiar with Singapore, Malaysia. Most of us are familiar with Boileau strength index and UCS test index. Okay, so here we have UCS and Boileau strength ratio is around 20. Okay, 20 UCS around 20 times higher than Boileau strength. Okay, the next one is the Brazilian tensile strength. Brazilian tensile strength. Okay, so this is a very rare testing method. This one we can do at the Nanyang Technology University, Singapore. Okay, from here we'll see that our rock pull-out strength is a bit higher. So this one we can excavate for the very big cavern in sedimentary rock mass. Okay, the next one is the tri-axial test. Tri-axial test, Singapore we cannot dig. Okay, so this all sample we send to China Wuhan University to test this tri-axial test. Okay, here we have the friction angle and cohesive strength. Okay. The next one is we measure, determine at the NDU. We have the raw joint survey, raw joint core sample from the core sample. We have the original raw joint survey. Okay, so this one we need to measure the direct shear tension on the raw joint. Okay, this is important for the tunnel crown and tunnel wall stability. Okay, we have higher friction angle. Okay, around more than 30 degree or 5 value and peak cohesion also kPa around 300 to more than 500. Okay. Then next one is we need to measure determine the geological strength index. This about what we have we have published whatever technical paper about the GSI. Okay, so geological strength index is a reduction factor. It is not like Q value or RMR. Q and RMR is for the raw mass property. Here is the whatever we have reduction factor. Reduction factor means, okay, let's say here we have you see this is the raw mass. Okay, we have integral. Okay, then after that we have raw joints and discontinuity and the fracture. Okay, when we send laboratory for UCS or Poilo strength, we can use the integral sample. So from that integral result, okay, Poilo strength and UCS represented for the index rock properties only, but this may not represent the whole raw mass. Okay, so this one we need to convert the index raw properties into the raw mass property. So to convert from index to raw mass, we need to determine the geological strength index. So this is the reduction factor. Okay, so geological strength index is earlier Mr. Hook, Albert Hook proposed in 1992. Okay, at the time, he didn't propose the name or the terminology or GSI. He used just the ratio only. After that, later on, he proposed the geological strength index. Geological strength index is, for us, geology is very easy. For here is the surface condition. Okay, the raw joint surface are very good, rough or weather or something like that. Then after that, from here, the block property. Okay, here you see the structure. Okay, here is the integral. Okay, only one joint or two joint. After that, more and more fracture. Okay, so this one, if we have what we call rock surface is very good, very rough, and very few joint. This is GSI value is 90. Okay, 90 means something like 90%. In that raw property, let's say 100 MPa. So this one, our raw mass, maybe 90% or 100 means 190 MPa, we can use something like that. If the raw surface is very poor, and also we have a lot of fracture, GSI value it become lower and lower. So this one is 10 means something like 10% of the integral. Okay, so earlier, this is only this is suitable for the granitic rock. Okay, later, okay, actually, Elba, who is a mechanical engineer. Then later, Mr. Marino is a Greece. He is an engineering geologist. I think he is a past president of IAEG. Now, he passed away already. Okay, so later, Mr. Marino, Professor Marino Elba, who presented the different type of next GSI determination chart. This chart is applicable for the sedimentary rock. Earlier chart is applicable for the igneous rock. Okay, so here from the Huron rock area, you will see the GSI value 45. For the some area here, you will see the 14. So 14, we have the GSI value here 25, something like that. Okay, so this GSI determination here, this is convenient for us, convenient for geologists. Okay, so the we determine the surface condition and rock block structure. Okay, we determine the GSI value. But this is good for geologists. But some engineer, they are not happy because they have no any what you call numerical value. Okay, so this one we then after that I search for the literature. We have some quantitative GSI value. Quantitative means we have the facts and figure. So this one I use an approach for the Hu, Chai, Professor Uluse, then Russell. Okay, from here, earlier is a qualitative GSI. This is now is a quantitative GSI. So I use the 4 approaches. Okay, so actually they are more or less the same. The same basic one, but the determination and the calculation is different approaches. Okay, different author call different approaches. So this one after that, the qualitative one and quantitative one, I later combine and compare. More, all of them are around plus or minus 10 only. Also, this one qualitative and quantitative can match. Okay. Then next topic, determination of raw mass property based on integral property. Okay, so this is the based on section 3 and 4. Okay, so this is the, if we are this, we need to what to convert from the integral to raw mass property. Okay, you will see here, if we send for laboratory for raw testing, we can send for only the integral sample, but this may not represent for the whole raw mass. So this one, to convert the representative value for the whole raw mass, we need to calculation. Okay, so for this calculation, we are using the, here you will see the GSI value. Okay, I is equal to integral, B is equal to raw mass. Okay, from here, we need to use a GSI. Okay, this D is equal to the excavation disturbance factor. Okay, so this also proposed by Elbahu. Okay, you will see here, if the excavation is very good condition, the disturbance factor is 0. But excavation is very damaged, the D value will become higher and higher. Okay, so you will see here, D is equal to 0.5, D is equal to 1. Okay, so this one is very nicely excavated. Here is the crown and wall is highly damaged. So this one T value is 0.5, something like that. Okay, from then we need to calculate for the from intact to raw mass property. But here equation is very complicated, but we no need to worry. We have the what do this we use the rock science rock data 3 program. Okay, that I'm using this program to determine from the integral to raw mass property. Okay, from here, okay, our input value is T value, excavation damage factor, then GSI value. Then we have the material ratio value. Then we import for the integral sigma value, UCS value, then material property. Then we can determine from integral to raw mass property. Okay, this is used for our numerical analysis. Okay, then geological structure control tunnel. Okay, mostly our tunnel are something like circular shape or horseshoe shape. Okay, our crown is normally we excavate or we design as the circular shape. But if we have the what they call strong bedding and strong joint, we cannot exactly get the circular shape because this corner one will be fall down. Okay, so this is the first approach in Australia. Okay, you see the Sydney Opera House. Okay, Sydney Opera House underground car park. They have this diagram. You will see all are horizontal pattern. So this one they are tunnel route also horizontally. The same apply in Singapore. Okay, our Jurong Rock Event project also. You see here is this is the before applying what you call rock support. Okay, so this is original condition after support. Here you will have the flat roof. Here also we will have the flat roof. Okay, we design and excavate at the circular shape, but because of the strong horizontal bed or horizontal joint, at the end we end up with the horizontal roof one. Okay, so this one we encounter this is the we have the good experience for that. Then another one is the numerical analysis. Okay, numerical analysis, we have the discontinuous analysis, continuous analysis, and three-dimensional analysis. Okay, so this all I use the raw science software, RS2 and RS3. Okay, discontinuity finite element analysis means in the model we directly use the bedding and raw joint discontinuity. Continuum means we didn't use the rock structure. We convert from the intact to raw mass property. Then we use the raw mass represented raw mass property to model the model. So this one we call the continuum. Then another one is three-dimensional. Okay, so here our given is 27-meter high, 20-meter width, and 340-meter long. Okay, so this one I use the whatever at first this is discontinuity analysis. Discontinuity here the model I use the horizontal bedding plane and two set of joint plane. So this is the discontinuity analysis. Okay, from here, okay, our excavation is step by step. We have the twin cavern. Okay, twin cavern means everywhere we have twin cavern. Okay, so I model something like okay step by step uh, excavation. Okay, from the model we can determine the horizontal displacement, particle displacement, and also the uh, uh, okay, then continue analysis. Continue analysis, earlier I have explained already. Continue analysis, we use the raw mass property. Okay, earlier we use the what geological structure in the model. Here, continue analysis, we convert into the representative raw mass property. So this one in the model, we didn't use any bedding plane or raw joint. So this is the difference between continuous and discontinuous and continuous analysis. Next one is a three-dimensional. Okay, so I model the RS3, okay, raw science software, then the model. Here, one thing interesting to know is here, our excavation phase is here. Okay, we excavated from here to here. Our current phase is here. But from three-dimensional model, we can excavate the inside, okay, unexcavated area also start displacement, start deformation. Okay, so this principle and this one, we can analyze in the three dimension. 2D, we cannot know. Okay, here you see our excavation phase is here, but this is the already excavated. This right-hand side here haven't excavated, stay fresh rock. But from the 3D model, we can know that the fresh rock excavated or area also start deform ready. So this is we need to consider in our done excavation. Okay, so in that we uh, monitor the displacement by using the what we call glass prison. Okay, we install a lot of glass prison on the roof wall. Then also all the value are around here, the around five millimeter. Okay. The next one is the last part is the basic principle for storing oil and gas in unlined rock cavern. Unlined rock cavern means our oil storage cavern, we are applying only the shotcrete and rubber only. We don't use any plastic or polythene or any other steel structure or we are not using the plastic sheet or steel structure. So we are just only using the rod bolt and shotcrete only. So this is what we call the unlined, no lining inside. Okay, so this one, the in unlined rock cavern, how we store oil and gas. Okay, so here, okay, you see here, this left diagram, you see, okay, this is the bucket. Okay, we put the Y in the bucket, but accidentally the bucket got one hole. Okay, so in that case, the Y will be spray leak out from the bucket. But if this bucket we put inside the water container, okay, like that, water container, okay, outside got water, okay, water density is higher than Y. So in that case, second diagram, water the Y cannot be leak outside. Why cannot be? Because the water density higher. This one the prevent why leak from the hole. We use this principle in the Y storage cavern. Okay, so this one we are artificially apply or artificially inject the water into the surrounding rock. Okay, so the surrounding rock is fully saturated. Fully saturated means something like this hole. Okay, this bucket we put into the water container. Okay, so this one we are applying the water, inject water into the surrounding rock. This is what we call the water cutting gallery. Okay, you see this diagram earlier I showed you already. Here we have this blue color is the water cutting gallery. You see here water cutting. Okay, so this yellow color is oil storage cavern. The green color is the water cutting gallery. So water cutting gallery we have the particle water hole. You see here particle water hole. Then also we have the some inclined water hole. Here we have the horizontal water hole. So that we are preventing, we are injecting water into the surrounding rock so that oil and gas may not leak out from the wide storage cavern. So this one we have the water tightness is important in the rock, the wide and storage cavern. Okay, so this one we have the horizontal water cutting and vertical water cutting. Okay, horizontal water cutting, vertical water cutting. Horizontal water cutting we are applying the water blanket on top of the rock cavern. Particle water cutting is okay. So this is the from one cavern to one cavern. We are preventing oil and gas to leak out. Okay, so this all are, uh, our publication one. Okay, if you have anything, you can refer from here. Okay, so this is end of my presentation. Thank you very much. At first, we have some problem for technical one. Okay, thank you very much. Thank you very much for all what I call SEGIM, organizing committee.
Okay, thank you so much, Dr. Kawin. I think I'll open only one question
Okay.
for the floor. If participants have any question for Dr. Kawin.
Yes. Okay. Okay, I cannot see where the question.
So far there's no. I think any last question for Dr. Kawin?
Hello.
Okay, yes, Dr.
Nini
Vini.
here. Yes, Dr. Kawin, thank you so much for your presentation.
Yes.
Actually, I was interested in the modeling that you showed just now,
Okay.
where you use the RS2 and RS3 software, right?
Yes.
So my first question, do you make any comparison with other software, like, we use more some sort of Plexis or Abacus, do you make any comparison to that?
Okay.
And
Okay.
yeah, and secondly, regarding your installation, do you allow for any convergence, and how much that the allowable convergence in your analysis? Thank you.
Okay. The first uh, The first question, okay, I use RS2 and RS3 for my PhD research, okay? So this one, my presentation is from my PhD research one. But our project, this RS2 and RS3, this project we, what do you call, engage NTU for the research purpose, okay? So NTU also, they use the, what do you call, RS2 and RS3, one team. Another team is, they are using the what UDEC. Okay, UDEC and the 3DEC. Okay, I also studied 3DEC before. Okay, so the NDU team have UDEC. I have another team have RS2 and RS3. But the result is depends on their analysis. Okay, UDEC, if I'm not wrong, I'm not very familiar with UDEC. UDEC, if I'm not wrong, UDEC is using the what you call representative raw mass property, something like continuous analysis. I I think I answer you the correctly because I'm not too familiar with the UDEC. Okay, so UDEC can model UDEC. I'm not sure UDEC can model what or discontinuity analysis or not. Okay, for
Yes.
me,
UDEC is the discrete element, right? So
yeah,
we need to
DM,
make the comparison. Okay.
yeah.
Mm.
Then second question, okay, from our analysis, okay, our maximum displacement or convergence is around 10 millimeter only. So this one so far, when we monitor using the the rock prison, okay, we encounter around less than 10 mm only, around 5 mm or 7 mm. So this one is the mesh our and what our numerical analysis and accurate what our monitoring data. I hope I have answered your question, Dr. Rini.
Yes, yes, indeed. Thank you so much.
Okay. See you in coming February. Yeah.
Okay, thank you so much, Dr. Kawin, for
Yeah.
your captivating presentation and also Dr. Rini for your question. Thank you so much again, Dr. Kawin.
Okay, I
Now,
will stop sharing.
okay, thank you. Now, let me introduce our very last speaker of the day. Again, Dr. Imam Ahmad Sadisun is now an Associate Professor of Engineering Geology in Faculty of Earth Science and Technology, Institute Teknologi Bandung, Indonesia. He received his Bachelor of Science and Master of Science in Geological Engineering from ITB respectively in 1995 and 1998. In 2004, he holds a Doctor of Engineering in the research area of rock engineering and engineering geology, especially related to swelling and slacking behavior of argillaceous rocks from Kyushu University of Japan. At present, he serves as the head of Engineering Geology Laboratory FEST IETP, research coordinator for landslide at Research Center for Disaster Mitigation ITB, chairman in Indonesian Society for Engineering Geology MGTI of Association of Indonesian Geologists, and representative member also president in the Indonesia National Group of International Association for Engineering, Geology and the Environment IAEG. He is now also involved in a panel of experts for Construction Services Development Board, West Java Province, Dam Operational Improvement and Safety Project, and Commission for Safety of Bridge and Tunnel, KKJTJ, Ministry of Public Work and Public Housing Indonesia. Now, without further ado, let us welcome Associate Professor Dr. I.R. Imam Ahmad Sadisun to give his presentation titled Engineering Geological Aspects of Infrastructures Development, Land Use Planning and Disaster Risk Management in Indonesia. Let us give her a round of applause.
Okay. Ms. Sarah, can you hear my voice?
Yes.
Yes, we can hear you.
Yeah, sorry. I have a feedback. Test. Okay, I hope you can hear my voice clearly. Okay, I would like to share my presentation material. Can you see my presentation material now?
Yes, can see you.
Okay, thank you. And I don't know about my video. Okay, no problem. I think quite similar with Dr. Kanwin. I omit my video in my presentation now. Well, good day, ladies and gentlemen, and Assalamualaikum warahmatullahi wabarakatuh. First of all, I would like to thank Pak Rashid Jafar, Pak Rashid Jafar, and also Mas Faruk Sahmi, ya, as chairman of Young Engineering Geology in Malaysia, and also honorable all invited speaker, distinguished guests, ladies and gentlemen. It is my honor to be a part of this event online seminar, yeah, for fourth Teams ASEAN Regional Conference that will be held at Kuala Lumpur, Malaysia next year on February. I hope I will attend that symposium. And also, thank you very much for this invitation for the committee. Now I would like to share our knowledge as well as our experience in general topic, I think, regarding engineering geology for infrastructure development, disaster mitigation, and land use planning in Indonesia. I little bit modifying the title of my presentation, but it's okay. And this is actually have already presented about 3 years ago. So I'm sorry for somebody here, you already follow my presentation before, but I will, and I give several updates for this presentation. I hope you can enjoy with my presentation. Well, this is presentation outline today. I would like to start with the introduction and some of a part of my presentation will be talk about the role of engineering geology firstly, and I would like to move to the birth of engineering geology in the world actually, and also in Indonesia in general, and then I will move to discuss about the engineering geology in infrastructure development, especially in Indonesia, and then how important the integrated disaster management into the infrastructure development, and finally I would like to linking engineering geology into the land use planning. Okay, as introduction, let me show an illustration of the role of engineering geology in the infrastructure development. As you can see here in the left side, for geologists, I think it is very common. You can many aspects of geology, including geological materials, geological structure, and also geological process. And the important one is the engineering geology critical interface, I think, between geology, data, and information into the land use planning, infrastructure development, and also disaster mitigation. So engineering geology must able to provide engineering solution to problem that arise over a geological aspect, including in infrastructure development, land use planning, as well as disaster mitigation. As you can see also in the definition of engineering geology in our association, in International Association for Engineering Geology and the Environments, that's already defined clearly. that we should give a solution of the engineering and environmental problem which may arise as the result of interaction between human and the environment in the wide space meaning. And then if we see the birth of engineering geology in specialist profession especially, we I think all of you already read in many textbook and also many writings paper that explain the birth of engineering geology, about William Smith's contribution for engineering geology, and he have credit in the creating of first national worldwide geological map. He is also known as a father of English geology, especially, and also father of modern geology. And I don't want to talk much about the William Smith. You can also identify the contribution how William Smith success in identifying rock layer that have the potential for landslide and handling that's problem. The another important milestone with regard the engineering geology, we also can consider with the beginning of modern of engineering geology with the publication we sometimes call as the first textbook for engineering geology textbook written by Penning, William Henry Penning. He is a pioneer of the British Geological Survey. And yeah, this is the books that written by William Pennings, and already many edition, and the last edition is the 2090 with the classic reprint by US Wentworth Press. Then in the birth of engineering geology, we also often read about the value of the St. Francis Dam in the USR, 1928. And at that time, actually, some experts also try to recognize and doing the engineering forensics. For example, come from the ransoms 1928 that explain with regard to this dam failure. They said that he said that there is no geological examination was made in the dam site before construction. So it is, I think, very important result for the ransoms regarding why the St. Francis Dam failure. And if you see more, actually there are many information with regard to this failure. For example, from the history video that give also a good history documentary with regard to this St. Francis Dam failure. And actually there is an explanation from this video, but I'm sorry, there is a problem in the audio connection from my computer, and it was explained that there are 426 lives were lost due to the dam failure, and it's also stated that this is worst man-made disaster in California during that time. And if we recognize from the San Francisco Dam failure, it's demonstrated that actually the need for the geological evaluation in deep evaluation, especially for foundation in the abutment. You can see here there are laminated mica skis, yeah, in the left abutment that have direction of the lamination quite same with the slope direction. So it is actually very easy for geologists to recognize the possible of the unfavorable condition. And then the second one, you can also see some conglomerate that usually come from the old alluvial deposit also, that covers the faults plane in the right abutment. So it is also can be said as a unfavorable condition when we deal with the foundation of the abutment. And okay, this is just the estimate of the surface after the failure occur in the dam, and you can actually looking for in detail about the San Francisco Dam failure in many references. Then I would like to invite you to know the development of engineering geology in Indonesia. Actually, we have I would like to explain about our first engineering geologists that developed engineering geologists in the first Indonesian independence. We have Professor Sampurno and also Mr. Porbo Hadiwijoyo. And in the important occasion here, Mr. Porbo Hadiwijoyo writes the status of engineering geology in Indonesia in 1970. That that's already submitted in the bulletin of IAEG. Yeah, also published by Springer. There are written here. You can see the contribution of both to pioneer in engineering geology in Indonesia, whether Professor Sampurno and Porbo Hadiwijoyo, with regard to their activities in the development of engineering geology. For example, Professor Sampurno have involved in the mapping and regional development for many cities in Indonesia, and the maybe best contribution in engineering geology is that in the restoration of the Borobudur temple. And Pak Purbo here actually works for geological agency. He involved in many development of dam in the first dam construction in Indonesia, and actually on the status of engineering geology of Indonesia that's written in the IAEG bulletin. They put the engineering geological map also and cross-section of Jatiluhur dam sets that constructed around the 1970. And in this good occasion, also I would like to introduce the big family actually in our laboratory. We have Indra and Dr. Randy that's already presented his experience, especially for Indra in the rockfall, and also actually he has interest in the debris flow research, and Dr. Randy also has interest in the development of landslide susceptibility map, and also with regard to the earthquake hazard map development in Indonesia. Okay, with regard to the education, actually in ITB especially, we have already engineering geology master program for the one option in our master program in 2007, and in 2019 we have a special pathway for engineering geology, especially including geotechnical pathway in the undergraduate program. In our association, Indonesian Association for Geology, we also have already Masyarakat Geologi Teknik Indonesia, or Indonesia Society for Engineering Geology. We established in this is a little bit mistake. Actually, we established in October 11, 2016. Yeah, as Brighton is in this declaration. Yeah, at that time I act as the vice chairman for this society. Okay, let's move in the key role of engineering geology in the infrastructure development. I think most of you already know that the engineering geology become the one of the most important due to all infrastructure take place either at on the below a surface, and most of infrastructure use of the earth's material. So I would like to in-depth give explanation in this important role or key role of engineering geology. For the worst, I would like to give an example of infrastructure take place in the earth surface. For example, here I put a bridge that set up in the Sewampu River of Binjai, Pangkalan Bradan, North Sumatra actually. And in this case, there is a potential of liquefaction. As you know, the Suchida graph here to know the potential of liquefaction of the material as a foundation of the bridge. We do analyze from this long span bridge actually, yeah, in relation to the foundation carefully due to the liquefaction potential, and also we'll try to use numerical analysis also. You can see the deformation analysis of group pile using 3D Plaxis software that show a good performance of foundation from total load after we do some analysis. Actually, we also analysis using fast Lagrangian analysis software for make sure that the foundation can better can make better for the liquid based on the liquefaction potential. In the second rule of the importance of engineering geology, I would like to give an example of how the engineering geology have the very important role in infrastructure that takes below the earth surface. We have here a tunnel that usually called as the sustainably and eco-friendly infrastructure. And quite same with the bridge, we have here the flowchart of the design procedure that suggested by Schubert and also modified by the Marinos 2021 that shows the definition of rock mass type is the most important one in that flowchart to make the geological model and make a definition of rock ground to the tunnel design. Then we can see here from the flowchart how the importance of engineering geology when we deal with the rock mass characterization, including rock mass behavior in the tunnel design, and especially to support in the choose the appropriate design parameter on the tunnel before we do some numerical analysis or analytical analysis on the design of the tunnels. Then actually in Indonesia there are many development of underground infrastructure, so I think the role of engineering geology for future drilling in the construction of the tunnel and other underground infrastructure will be increased. And the last key role of engineering geologists is regard to the Earth's material. And here I just give an example when the geology concerned with the construction material, especially in the concrete aggregate. And actually, there is important aggregate analysis based on the geologic point of view. For example, here we should do aggregate petrographic analysis when performed from the quality of the aggregate. One of the important from the choosing the aggregate is the potential of alkali aggregate reaction. I have also one paper, I think, with regard for analysis aggregate alkali aggregate reaction that published in 2000 with our colleagues Pak Edi Sucipta. Yeah, you can find in Google Scholar and any reference websites. Well, let's move in the importance of engineering geological investigation when we deal of to the development of infrastructure, I think. In this regard, I would like to adopt the statement from Hooks and Palmery that say that the unforeseen geological conditions and some geotechnical problem usually arise and cause or give a contribution to the cost of run and also a schedule delay for large infrastructure project. And they also suggest that the best solution is in this regard is conduct geological investigation as early and as accurately possible. I think this is the important to be keep in mind that the contribution of engineering geology usually not in the early condition of the project and not so accurate. Yeah. Yeah, I would like to show some aspect of engineering geological investigation. Usually, I also call as a pentagonal aspect in the geological investigation, starting from the geological condition until the geological hazard potential. You can see five aspects, the importance of five aspects here. And we should characterize based on the potential, or sometimes we call as also geobarrier from the unfavorable condition, and we should give evaluation for that entering geology characteristic. And in this regard, we also should keep in mind about the state of the construction, starting from the regional appraisal until to the operation and maintenance, with the contribution of entering geological map into different scale of the map. It is important, and in this regard, Indonesian have already standard SNI 03 2000 and 2002. We actually would like to update this standard for the near future. And with regard to the entering geological map, I think you all entering geologists already know about the guideline that published by UNESCO Press. It is old guideline, but it is very interesting to still use this guideline. Then already updated by colleges from the British Geological Society into textbook. You can see here the textbook in that already published 2002 to replace the guideline from the UNESCO Press. And how about the disaster management or disaster hazard potential or geological hazard potential? We deal into the infrastructure development. As you know, Indonesia in the triple junction of the world major plate and also in the humid tropical region. So that's why our country, especially in Indonesia, I think very high, high to very high, I think, risk or various type of geological disaster. And when we deal with the earthquakes, as already explained by Dr. Randy, yeah. So I think we should in Indonesia make a good analysis and good preparation for the deal with the infrastructure development. Yeah, I would like to just remind again how to infrastructure can be made due to the earthquakes. And in Indonesia, actually, we always make a routine improvement on seismic hazard map, as also mentioned and explained by Dr. Randy. Here we already have already updated the building and infrastructure code. That's actually always deliver in many seminar, and this updating led by our colleges in civil engineering, yeah. But the involve of our colleges, such as Dr. Randy, that have a background of geologists, I think is very crucial, yeah, because we always also do update the source of the earthquakes, and sometimes we also do some analysis with regard to the site-specific analysis with regard to the earthquake hazard. And this is the last map that published by the PUSGEN that already Dr. Randy also mentioned, Pusat Studi Gempa Nasional in Indonesia, that very active into the updating of the earthquake hazard map in Indonesia. And we put the implementation of the hazard map into the many type of infrastructure development in Indonesia to achieve the resistant building and infrastructure from the earthquake hazard potential. And talk about the earthquake hazard, we should also concern about the peak ground acceleration at the ground surface based on the site class. Here in Indonesia, we has already published the new site class map atlas for all the country. So anyone who interests with the set map atlas in Indonesia, you can download by yourself. Published by the Center of the Volcanology and Geological Hazard Mitigation Geological Agency of Indonesia. Okay, actually, this just I would like to explain how we develop the atlas of the map with regard to some disaster potential, especially geological disaster potential in Indonesia. For example, here we see the liquefaction susceptibility analysis that suggested by the Kramer 1996 that this method actually initial method for Indonesian government to create the map that's already published in 2019. And also next week actually we would like to discuss again to update this map and make a special guideline to make the more detailed map with regard to the liquefaction susceptibility map into more detail. And then we also have actually landslide susceptibility map that already also published in each regency or city in Indonesia. And next week, we also want to look at the standard. We already have a national standard to make this map. So everybody want to contribute, make the map into the detailed scale, and they can see the standard to follow and to make the quality of the map can deal with the standard that did from the SNI 2016. Yeah, I forget the number of the SNI. And finally, I think
sorry, doctor.
Okay, this is the maybe last part of my presentation.
Okay.
Yeah.
So I'll give around 1 minute because we have overrun our event. So yeah, you can wrap up your presentation.
Yeah. This is actually my this is many map that's already published by PUSGEN and also Geological Agency and also BMCG of Indonesia that have I think good contribution in deal with the disaster management in Indonesia. And finally, I think it is important one aspect of geological data and information bring to the land use planning. I don't want to talk much with regard to the land use planning, I think most of you already familiar when we try to analyze using multi-criteria, and now we have many methods with regard to the statistical analysis and also deterministic analysis when deal with the multi-criteria. One of the method that's very common in doing analysis from the geological data into land use planning, and we try to use this all data for applied in many places in Indonesia in terms of land use planning. I think that's all my presentation. I'm sorry for maybe quite general presentation, but I would like to make sure that the engineering geology in this case will provide best practice and guidance for infrastructure development, disaster management, and land use planning in Indonesia. Thank you very much for your kind attention, and I would like to bring back my time to Ms. Sarah. Thank you.
Thank you so much, Dr. Imam, for your captivating presentation just now. We would like to excuse for Q&A session as we have overrun our event today.
Okay.
So
Thank
if
you.
any of
Sorry.
the participants have any questions to Dr. Imam, you may email him, and
Yeah.
Dr. Imam may reply outside of this event. Thank you very much again for the presentation.
Thank you.
So before we end our event today, I would like to call upon Mr. Muhammad Farooq Shahmi, Chairman of the Young Geo Professional Group of SEGRM, to give his closing remarks.
Okay, can you everybody hear me? Yeah.
Yes, we
Yes.
can
Thank
hear you.
thank you, Puan Sarah, and everyone. So we just ended our seminar for today. I am very happy. First of all, I would like to reach out my thanks, my gratitude to all the presenters, Pak Indra, Mr. Johan, Dr. Randy, Pijal, Abdul Rashid, Dr. Kawin, and Dr. Imam, and also Mr. Shazwan from various background of engineering, geology, also geotechnical, including from not only from Malaysia, also from Singapore, and from ITB Indonesia. And then we have our participant from all over the world, including in Nepal, in Pakistan. So I am very happy that we have been successfully conducted this seminar. So as you all know, I would like to share the circular brochure for our next event. So this seminar is specifically actually to promote our event, which will be held on the 27 to 29 of February 2024 next year. We are still opening our submission, the submission for the abstract. Everybody are welcome to send their abstract and present it. So we are inviting a lot of international speakers, as per mentioned by Mr. Abdul Rashid. So we have the chairman of the IAEG himself, Professor Dr. Marinos, Professor Dr. Fakuan Wu, which is the secretary of the IAEG, and also and then we have Anne Williams, the past president for Australasia, and we have the vice president of Asia, which is all of here. We reported to him, Professor Dr. Rajan Kumar, and then the president of Japan Society of Engineering Geology, Pashiko Osada, and others from Hong Kong also, Professor Dr. Louis Wong, from Bangladesh, and also from Malaysia. So we have a very list of esteemed keynote speakers. I am hoping that everybody, not only from Malaysia, but also from Indonesia, Singapore, maybe Thailand, Nepal, Pakistan, all over around the world can join our seminar next year. And of course, and we have a special session actually, one special session on a day before. Sorry, let me go through. Yeah, a day before the conference, which is on the 26th. We will have a special session for young engineering geologists, which will attended by Dr. Stratis Karentalis from the chairman of IAEG, Young Engineering Geologist IAEG. He's from Greece, but actually he is working as a lecturer in USA. He will be accompanied by another representative, but I haven't received the name. So we have a special session there for young engineering geologists. I would like to welcome everybody. This is open, free for everybody to come. We have a discussion and then maybe a presentation and maybe like a ice-breaking session, just to meet around new people and getting to know new people, and maybe at the same time we try to improve our technical knowledge in engineering geology, sharing with everybody. So I don't want to talk anymore, much more. We will have to end this seminar. I thank you everybody to attend. Those who are attending here, this seminar, and hoping to see you in the next year at Asia Regional Conference of IAEG in Kuala Lumpur, Malaysia. Thank you very much.
Thank
Sarah,
you
I give
very
it back to you.
okay, sorry. Thank you very much, Mr. Muhammad Farid Shahmi, for the given speech. So as the saying goes, to every beginning there is an ending. And now the seminar has come to its end. Once again, thank you everyone for gracing today's seminar with your presence. We truly appreciate it. We would like to invite all of you to participate in 14th Asia Regional Conference of IAEG 2024 at University of Technology Malaysia, Kuala Lumpur, Malaysia. For your information, again, due date for extract submission is still open. Will be on 30th November 2023, end of this month. We also kindly log on to our website www.arc14.asia. Again, www.arc14.asia to download the brochure and for more information. So on behalf of the organizing committees, I would like to apologize for any mistakes and issues happened throughout the event. Also, the recording of this webinar will be provided later to our participants. Hence, I end my duty as Master of Ceremony of today's event with Wassalamualaikum warahmatullahi wabarakatuh and a very good afternoon to all. Thank you very much.
Thank you very much. See you.
Thank you.
Thank you. Jumpa nanti. Bye-bye.
Everyone.